Hello, everyone. I'm Olympia. Thank you for being here with me in this wonderful place called Lights Out Library. And I have a great story to tell you. The first leg of our trip begins close to the sun, near the smallest and fastest planet of the system, Mercury. Mercury is only about twice as big as the Earth's moon, and there are satellites that are actually bigger than Mercury, like Ganymede, the moon of Jupiter, or Titan, the moon of Saturn, both of which we will explore in a future story. But Mercury is considered to be a planet because it follows its own orbit around the Sun. It is not the satellite of another planet. Its mass is also greater than any of these satellites because Mercury is denser, with a density similar to Earth's. It is believed that Mercury is made mainly of metal, 70% iron in fact, and the rest, about 30%, silicate material, which we generally call rock. As we're going to see, conditions on the surface of Mercury are strongly influenced by its proximity to the Sun. But how close to the Sun is Mercury exactly? On average, the distance is about 35 million miles or 58 million kilometers. For comparison, the Sun has a diameter of almost 1.4 million kilometers or 865,000 miles. So it's actually not that close proportionally. If the Sun were the size of a basketball, then Mercury would be a small grain of sand, but several steps away from the basketball. Still, this raises a question. If Mercury is comparatively small, but with an enormous mass, the Sun, after all, has a huge gravity well, which is the amount of gravitational pull an object in space is able to exert. How does Mercury keep its distance from the Sun instead of being pulled into it and swallowed whole? This brings us to the subject of speed and orbits. Mercury travels in space around the Sun at a high speed. Its velocity is 48 kilometers per second, about 30 miles per second. By comparison, Earth travels at 30 kilometers per second. The general rule is that the further the planets are from the Sun, the slower they are on their orbits. The farthest one, Neptune, travels at only 5.4 kilometers per second, almost 10 times less than Mercury. And this is not a coincidence, because an orbit results from an equilibrium. There are two main variables to consider in a star system like ours when it comes to orbits. There is the gravitational pull of the huge mass that is at its center, which pulls the planet, and then there is the object's velocity, which tends to push it away. It is a centrifugal force. Without the mass of the star at the center pulling them, planets would just escape. Their speed would surpass what is called the escape velocity, which is to say the speed above which an object can break free from the gravitational pull of another body. Their orbits form thanks to this equilibrium. The balanced push and pull between two bodies. There are bodies that sometimes do escape the systems where they first appeared and travel between stars, sometimes even between planets. We know there are lone planets which most probably formed in a star system and were expelled from it. Because even though orbits can last for hundreds of millions of years, billions even, they can be altered by other bodies, sometimes that, for example, can make a planet or a satellite accelerate and break free. This equilibrium does not mean that the orbit is a perfect circle or that the speed is constant. Most orbits are actually elliptical. They look more or less oval, and that's particularly the case with Mercury. When the planet comes closer to the Sun, the gravitational pull tends to make it accelerate, which means that it is pushed away. Its higher speed allows it to go farther from the Sun, but not far enough and fast enough to break free from it. So, after traveling following a curve that makes it move away, it is pulled back, it reaccelerates, and so on. The cycle repeats itself. In the case of Mercury, it repeats itself in 88 of our Earth days. So the Mercurian year, one revolution around the Sun, is 4 times shorter than that of the Earth. Now, we say that planets like Mercury revolve around the Sun. That is true, but it's not 100% accurate. What planets and everything in the system revolve around is not the star itself, but around the center of mass. The Sun accounts for more than 99% of this mass, 99.8% to be precise. So obviously it determines very strongly the center of mass, but the real center of mass in the system is not the center of the Sun. Each planet also has a little gravitational pull and drags the center of mass towards it. Of these planetary influences, the most important one in our solar system is by far Jupiter, because it is the largest planet. Jupiter, in fact, is more massive than all of the other planets combined. Now, as it happens, the center of mass is generally inside the Sun, because planets are scattered around it, so their respective pools tend to cancel each other. But sometimes the center of mass can be outside of the Sun. If we imagine, in an extreme case, for example, when all planets in our solar system are on the same side of the Sun, as a result, all pull more or less in the same direction, which is something that can happen if the planets were to be aligned on the same side. The center of mass could be at a distance of 2 suns' radius from the Sun, or 1 diameter. It is not much in galactic terms, but it does lead to another geeky question. How often, if ever, are the 8 planets of the solar system aligned on the same side of the Sun? Actually, This is extremely rare, and technically the 8 planets cannot perfectly align because their orbits are not exactly on the same plane. They are all slightly tilted, so at no point could we draw a straight line that would go through the centers of each planet because of the differences in planes. But if we simplify and just imagine that the planets are aligned, looking at the solar system from above, we can see that it probably never happened, and it is unlikely to ever happen before our solar system disappears. Why? Because an alignment of just the 3 innermost planets of the system, Mercury, Venus, and Earth, happens only once every 40 years. The chance of having Mars, the 4th planet, on the same arc at this precise moment is minuscule, and the alignment of the 4 first planets is only possible once every several thousand years. And as you add more planets, Jupiter, Saturn, Uranus, Neptune, which are slower and slower with larger and larger orbits, the probability that they could all align in the same arc at the same time decreases very quickly. In other words, the number of passes you have to wait for this alignment to happen increases exponentially. I found a paper by a mathematician who calculated that the alignment of the 8 planets could only happen once every 400 billion years. But the solar system is thought to be only 4.5 billion years old, almost 100 times less than that. And following the Big Bang Theory, the universe as a whole is less than 14 billion years old. So it is unlikely that the alignment of the 8 planets that can happen every 400 billion years ever took place in the first 4.5 billion years of the solar system. Maybe the odds are around 1%. Also, the odds are that it will not happen before the sun dies and the system disappears with it. But still, the point was to tell you that the center of mass moved a bit over time, and that this is the real pivot around which planets revolve. Now, let's take a look at Mercury itself. Like other rocky planets, Mercury has a solid crust and a dissociated structure inside, meaning that elements are organized in layers with a mantle and a core. And as you approach the center of the planet, pressure and temperature increase. I told you earlier that Mercury is 70% metal and that it contains proportionately a lot more iron than any other planet in the solar system. This is a bit of a mystery in itself because why would a particular planet accumulate a lot more iron than others in its formation process? Rocky matter in the solar system has a certain ratio of silicate and metal that can also be found in rocky planets like Earth or Mars. So, why does Mercury differ in its composition? The first theory to explain this, the most widely accepted at this point, is that Mercury was once bigger than it is now. Several billion years ago, and at that time its mass would have been more than twice its current mass, with a metal-silicate ratio similar to other rocky planets. But the solar system was still in its early stages, and there would have been a collision with a planetesimal, that is to say, a fairly large object, formed by the aggregation of rocks and dust that crossed Mercury's trajectory. Based on models, this planetesimal would have been several thousand kilometers across and about 1/6 of Mercury's mass. The collision between the two objects would have been cataclysmic and would have stripped away much of Mercury's original crust and mantle, that is to say, its rocky components. So Mercury, as a result, would be so rich in metal, not because it attracted more iron than other planets, but because it used to be a bigger planet that lost much of its rock and kept its metal. But this is just a hypothesis, and there are others. The second one has the same starting point. Mercury was more than twice as massive in the early stages of our solar system than it is today, but the loss of its rocky material would not have come from the collision, but rather from solar activity. The proto-sun, which was still forming, would have been larger than today. Its gravitation made it contract to its current size over millions of years. So the sun would have been larger at the time, and as a result, temperatures near Mercury would have been around several thousand degrees. This would have vaporized the rock at Mercury's surface, forming an atmosphere of rock vapor. And this atmosphere would have been lost, carried away by solar wind, that is to say, the stream of particles that the sun produces. So this is yet another potential explanation for the loss of Mercury's rock that would explain why it contains so much metal proportionally. The third hypothesis proposes that Mercury formed as a metal-rich planet from the start because of its proximity to the sun. The huge cloud of gas that would have become the sun would have caused drag on the particles from which Mercury was forming, was accreting. This would have made lighter particles to be expelled and swallowed by the sun instead of being gathered by Mercury, whereas heavy metallic particles would have remained available, and as a result, Mercury would have ended up with more metal than rock in its structure. In any case, this happened several billion years ago, and today Mercury presents a surface that is similar in appearance to that of the Moon, with large plains and lots of craters, which always indicates that the body is geologically inactive. The surface material is not renewed by volcanism or plate tectonics like on Earth, but instead it remains static, and only impacts from asteroids can modify its appearance. Due to the proximity of the sun, it makes sense to anticipate high temperatures on the surface of Mercury, and indeed this is the case, but only on the parts that are directly exposed to the sun. Mercury can also be an intensely cold place. Near its equator and during daytime, on the side of the planet exposed to sunlight, the temperature rises up to 700 kelvins, which is about 800 degrees Fahrenheit and more than 400 degrees Celsius, about twice the temperature of a cooking oven. But the same regions at night, when they are plunged into darkness, fall to only 100 kelvins, which is minus 280 Fahrenheit or minus 173 Celsius. That is to say, cold enough to freeze water instantly. I'll tell you another time about conditions on Mars, which are harsh, but almost welcoming compared to Mercury. And what makes Mercury even more inhospitable is that a day or a night lasts a very long time on the planet. The planet revolves rapidly around the sun. As I told you before, every 88 days, but it rotates, it spins very slowly on its axis, in a way that is locked to the sun. Every time the planet completes 2 revolutions, 2 orbits around the sun, that is to say, 2 Mercurian years, the planet rotates only 3 times on its axis. For comparison, when the Earth completes 2 orbits, 2 Earth years, it rotates more than 700 times on its axis. But Mercury only 3 times. It is very slow at rotating. Another way of saying this is that one single day on Mercury is the same amount of time as 58 Earth days, which also means that any point on the equator of Mercury can remain exposed to the sun for a very long time, or for an equally long time stay in the dark. 176 days, 2 Mercurian years. The time for the sun to rise, stay in the sky, and set is actually longer than a year due to this combination of rapid orbital velocity and slow spinning. 1 year on Earth is 365 days, but on Mercury, 1 year is half a day. There are also regions of the planet around the poles that are constantly in the dark or near dark, and where temperature never rises much. Probes sent in the past decades have shown that there is likely ice, probably water ice, that stays permanently frozen around the poles of Mercury. This shows that despite its proximity to the sun, the planet is not just a burning hot desert of plains and craters. The hottest planet of the solar system is actually not Mercury, but Venus. If you find Mercury hostile, just wait for Venus, because it is worse. And so let's continue with our journey to our second destination, which is also the second planet from the Sun in our solar system. At first glance, Venus and Earth look like twin planets, almost the same size. Earth is just a touch bigger. The 2 planets are not that far apart, and actually, there may have been a point in the distant past when Venus looked more like Earth than it does today. But nowadays, the conditions at their surfaces could not be more different. We saw before that Mercury is just over 36 million miles from the Sun, which is just an average, of course, because its orbit is elliptical. Venus, by comparison, is nearly 109 million kilometers, 68 million miles away, almost twice as far. The orbit of Venus happens between the Sun and the Earth's orbit, and this means that, seen from Earth, Venus is never very far from the Sun, and when it is not hidden by the Sun's rays, it is not hard to see. After the Sun and the Moon, Venus is the most visible, the brightest object in our sky, and its visibility is increased, not just by the relatively short distance on an astronomical scale, but also because of a layer of very reflective clouds in its upper atmosphere. Mercury, the Moon, or Mars barely have an atmosphere compared with Earth, but Venus, on the other hand, has the thickest, densest atmosphere of all the rocky bodies in our solar system. The clouds that enshroud it and make the planet look like white when seen from space are composed primarily of sulfuric acid. But this is just a taste of what lies beneath. The atmosphere on Venus's surface is so dense that the pressure is more than 90 times what it is on Earth. For comparison, it is the equivalent to the pressure of being about 3,000 feet, 900 meters underwater. That's an amount of pressure that human bodies cannot stand, obviously. Now, there are submarines that reach this depth and deeper, so it's not impossible to imagine a man-made vehicle resisting the pressure on Venus's surface. But an additional problem would be the heat. The mean temperature at the surface is estimated to be more than 700 kelvins, that is, 460 degrees Celsius or 860 degrees Fahrenheit when exposed directly to the Sun. Why is Venus so hot? Again, it's because of the atmosphere. We'll come back to the reasons why Venus ended up with such a dense atmosphere. But if we examine its composition, it is primarily made of carbon dioxide, 96% carbon dioxide, plus 3 or 4% nitrogen and traces of other elements. And we know it rather well because Venus was one of the first targets of space exploration. In the past, the Soviet Union had an ambitious program to explore Venus in the 1960s, and they sent several probes. And these probes didn't survive long in the atmosphere given the conditions, but they did last long enough to send back a lot of valuable information. And since then, more and more information about Venus has been collected, including by NASA, with a probe called the Magellan Orbiter. This probe was able to map the surface using radar since it's hidden from visible light. The carbon dioxide at the surface of Venus is in a state that we don't normally encounter on Earth. It is called a supercritical fluid, which means it is not just gas because it is very pressurized, it's also very hot, but not to the point of being solid. It has passed the critical point of pressure and temperature where it could be a gas, but there is not enough pressure to make it a solid. So it exists in an intermediary state beyond the gas and liquid phases. And this is what we call a supercritical fluid. It is believed to be rather common in the atmospheres of gas and ice giants, Jupiter, Saturn, Uranus, Neptune, and also on Venus. On Earth, though, supercritical fluids don't normally occur naturally because of a different set of conditions, except maybe for water at the exit of some hydrothermal vents. Hydrothermal vents are like natural chimneys that eject very hot water that is heated by the temperature of the Earth's mantle. This water is very hot, several hundred degrees, when it comes out of the vent. So, were this superheated fluid be ejected at the Earth's surface, it would be steam. But at these depths it cannot be steam because there is too much pressure. These vents are deep underwater. This fluid cannot be just liquid either. It's too hot for that. And at the same time, there's not enough pressure to make it solid, to turn it into ice. So instead, like on the surface of Venus, it is in a supercritical state. This doesn't last long, though, because once it's ejected into the much cooler surrounding water, it cools down quickly and becomes just a liquid. It is hard to imagine the texture of a supercritical fluid. We are not used to it at all. But in any case, you would not want to experience it because if you plunged your hand into a supercritical fluid, your hand would be both burned and crushed at the same time. This gives you an idea of the kind of environment at the surface of Venus. And Venus's atmosphere is also responsible for the heat. It is so dense that it doesn't allow any heat to escape. It creates a massive, extreme greenhouse effect, the strongest we know of in the solar system. Venus did not form with such a thick atmosphere. Typically, the gases that compose the atmosphere on a rocky planet can come from an asteroid impact. They are liberated and stay because of gravitation, or from degassing from the planet's crust and mantle, which is when gas is released at the surface. Typically, what happens with volcanic activity. This atmosphere then stays in place around the planet when the planet is massive enough to retain it due to gravitation, and when it's not carried away or ejected into space by collisions or by the solar wind. A magnetic field like the one that surrounds Earth, its atmosphere. Venus does not have a magnetic field, so gravitation explains how the atmosphere is able to stay with the planet. Earth and Venus have similar masses. I told you Earth is just a touch more massive, so they also have quite similar gravitational pools. Given this set of conditions, how did Venus end up with this crushing atmosphere when Earth did not? These are just hypotheses, but studies have suggested that several billion years ago, Venus could have had an atmosphere similar to Earth's early atmosphere. In these conditions, there could have been substantial quantities of liquid water on the surface, and why not? Life could have appeared in these oceans if they existed. But what would have ultimately doomed Venus would have been its proximity to the Sun. The distance from the Sun to Venus is 70% of the distance from the Sun to Earth. This means Venus receives more energy from the Sun. And as the Sun only gained in luminosity in the first 100 million years of our solar system, any water on Earth would have entirely evaporated. This would have accumulated greenhouse gases in the atmosphere. Water, as gas, as vapor, has a greenhouse effect, and once it passes a critical point of greenhouse effect, the heating of the planet would have snowballed into a loop. The accumulation of heat at the surface would have been released when more greenhouse gases, thickening the atmosphere and making it even hotter, and so on in a cycle. At this point, it is hard to imagine any life on the surface of Venus, but if there is any, and this is purely speculative, because we have no solid evidence of life on Venus at this point, it could not be on the surface, but would have to be higher in the atmosphere, in the upper cloud layers of Venus, about 30 miles or 50 kilometers above the surface, because there, temperature and pressure are lower and actually not that far from terrestrial conditions. But this environment is also very acidic, so any forms of life in that environment, if they exist, would have to be able to thrive while floating in a type of environment that has no equivalent on Earth. And actually, the clouds are so dense that things could float on them. Venus was one of the first sources of inspiration of terraforming, or at least the installation of human cities in other planets. Another effect of Venus's surrounding atmosphere is that the temperature is about the same everywhere on the planet. There are no large differences between the equator and the poles, like on Earth and other planets. But there are still differences in temperature due to differences in altitude. Venus has a geography with plains that cover 80% of it, which have a volcanic origin. There are also apparently active volcanoes on Venus, and the sulfuric acid we talked about in the clouds of the upper layers of the atmosphere would have come from volcanic activity. There are also highlands, impact craters too, on the surface, but no small craters because, with such a dense atmosphere, it takes a bigger asteroid to penetrate it and to impact the surface. Many meteorites, like the ones that sometimes strike the Earth's surface, would be destroyed, vaporized long before impacting Venus. But there are larger impact craters left by bigger asteroids. The images we have from the surface of Venus are not actually photographs. They are radio maps that have been colored in false color. but they still give us a pretty good idea of what the surface looks like. Venus is probably similar to what the Earth would look like with no water, no life of any kind, and constantly plunged into darkness because the sunlight cannot reach the surface. Why don't you make yourself comfortable? Grab a drink if you like, or find the right position in your bed because we just took off for a new space journey. And this one will take us to Mars, the first manned mission to Mars ever. And given that we do it by imagination, I can already tell you that everything's going to work just fine. We'll be back on Earth, safe and sound. Along the journey, to entertain you during the trip, I will tell you about our destination, the red planet, and the challenges to overcome travel to Mars, land, stay, and come back. From the energy necessary and the distance to radiation or cohabitation of a small group of astronauts. For a several months long journey, we will also talk about terraforming as a concept and how it could be applied to Mars and many other things. So there's a lot to discuss, and Earth is already getting smaller, and we have crossed the orbit of the Moon. But there are still millions of miles to cross before we reach Mars. In future space cruises, we will travel faster than light to reach exoplanets and galaxies. Such speeds defy the laws of physics as we know them, and there is good reason to estimate that they cannot physically be achieved. But tonight, we are traveling at just a few percentage points of speed of light, which will be enough to complete the round trip in about an hour. Such a speed has never been reached by men, but it is theoretically possible, at least. So, what is the distance between Earth and Mars? There isn't a single answer to this question, because the distance is constantly changing. Since you tuned into this story, the distance has changed by thousands of miles as the two planets follow their orbits around the Sun at high speed. Sometimes they are on either side of the Sun, and when this happens, Mars is invisible from Earth. When the two planets are on opposite sides of the Sun, the distance is the maximum and it reaches 400 million kilometers. This would be like 10,000 times the circumference of the Earth. But there are also times when Mars is much closer, when Earth and Mars are aligned on the same side of the Sun, and in this case, the distance drops to about 55 million kilometers, almost 8 times less. This is less than 40 million miles. About every 26 months, Mars reaches what is called a close approach to Earth. This close approach is an advantageous moment. That is the right moment to send missions to Mars. But the distance when a close approach happens is not always exactly the same, because it is not that simple. The two orbits of Earth and Mars are not exactly on the same plane. They are slightly tilted with respect to each other, and the exact shapes of these orbits constantly change because they are influenced by the position of other bodies, especially Jupiter, which has a significant influence on the orbit of Mars. At the scale of the solar systems, calculations have to be made to take into account velocities and the influence of all bodies involved. Therefore, there is a lot of modeling and mathematics involved in making accurate estimates. This is crucial because a probe cannot afford to miss its constantly moving destination, which can be millions of miles away. A good understanding of orbital speeds and all the factors that impact them is necessary to prevent such mishaps. With all these elements at play, not all close approaches between Mars and Earth are exactly the same. In 2003, Mars made its closest approach to the Earth in 60,000 years, and it won't be that close again until the year 2287. In the meantime, humans will have to travel a greater distance to close the gap between Earth and Mars. NASA has 2 missions related to Mars in the works. The Artemis mission is meant to establish a U.S. spaceport on the Moon for future deep space launches. The Artemis mission is meant to establish a U.S. spaceport on the Moon for future deep space launches. The Artemis crew of 3 Americans and 1 Canadian will fly by the Moon in 2024, then land on the Moon in 2025. The first time humans will have done so since 1972. The second mission is known simply as the Mars Sample Return, a campaign to bring samples of Mars soil and rocks back to Earth. Given that probes or spaceships need to return, these missions will need to be planned over several years. It is not possible to just arrive, land on Mars, take samples for a few weeks, and then immediately return, because during that time spent on the planet, the distance from Earth will have increased by millions and millions of miles. And the distance, time, and space are not the only elements that matter. The energy needed to land and return is maybe even more important. Even the shortest trip is not necessarily the most realistic or achievable. Storing fuel is complicated after all. It takes up a lot of room and it's very heavy, thereby requiring energy in the form of fuel to transport fuel as part of a spaceship's cargo. As soon as space flight began, astronomers and engineers started studying the most efficient paths into space. When it comes to energy consumption, an economical way of traveling between planets is to jump from one orbit to another, following an elliptical orbit. This kind of transfer is called the Hohmann transfer orbit. This is the orbit followed, for example, by the InSight probe sent by NASA a few years ago. It implies approximately a 9-month travel time from Earth to Mars, then stay about 16 to 17 months on Mars, waiting for the next transfer window. Another 9-month trip to return to Earth. That is to say, 3 years in total for the round trip. A method that can help consume less energy when approaching the target planet is called ballistic capture. And what is it? When spacecraft use the Hohmann transfer orbit, it typically requires the spacecraft to burn fuel in order to slow down at the distant planet, because when the ship approaches it, it travels faster in space than its destination. It has to catch up with it. The fuel necessary to slow down has to be transported all the way from Earth, which adds to the cost and complexity of the craft. However, with the method of ballistic capture, the spacecraft is just placed in advance on the orbit of its destination planet before the planet arrives. When the target arrives, the craft is captured by the planet's gravity and can pull itself in orbit around it with small thrusters for adjustment. Another possible method to slow down spacecraft when they reach their target is a maneuver called aerobraking. Aerobraking consists of flying the craft through the atmosphere, so it has to be a body with an atmosphere at the low point of the orbit. The friction and drag slow it down, and the advantage is that this method uses the environment and doesn't consume more energy than necessary to position the craft on the right orbit. All of this gives you an idea of the variety of mission plans and possible paths that have been imagined and tested. We are now halfway to our destination. So before we talk about landing and the environment we will find on Mars, let's take a look at the formation of the planet and what it is made of. As you may know, the dominant theory about the formation of planets in our solar system is that they all started with a large accretion disk, a disk of gases and dust that was kept together and put in motion by gravitation. Most of the mass of matter concentrated in the center to form the sun, but not all of it. The periphery of the new star was still filled with matter, with dust in orbit around it. Through collisions over millions and millions of years, this dust snowballed into bigger and bigger rocks and boulders. After millions of revolutions around the sun, bigger rocks and protoplanets progressively cleaned up their orbits of dust and smaller bodies by absorbing them or turning them into their satellites like Earth. This process is believed to have been completed about 4.5 billion years ago for Mars. At this point, rocky planets in the solar system had eliminated most of the smaller rocks and boulders in their orbits, and they had taken a ball shape. This globe shape occurs because of gravity. Above a certain size, bodies become round, whereas smaller objects like asteroids or comets can't maintain other shapes. They are not large enough or massive enough to form a ball of matter. It is difficult to determine the history of Mars from Earth. On our planet, we can study the geological timeline by analyzing the layers of rocks and minerals. On Mars, nothing like that has been done yet. A few samples of soil could be analyzed by probes, but nothing comparable. However, it doesn't mean hypotheses cannot be made. The age of the surface of the planet can be estimated by counting the number of visible craters. A higher number and density of crater points to older terrain. However, Mars has also experienced intense volcanism along its history, and volcanism resets the surface terrain. It also has glaciers, winds, and possibly running water in the past, so craters may have been erased. With these limited means of estimating the age of the surface, the oldest part is believed to be in the southern hemisphere. The surface there would be about 3.8 billion years old. In the northern hemisphere, the landscapes are dominated by large plains that would have appeared later after the last waves of bombardment by asteroids. It is believed that after its formation approximately 400 million years ago, 4.5 to 4.1 billion years ago, Mars had a dense atmosphere. This atmosphere was formed as a result of asteroid and comet impacts, as well as gases escaping from the planet's mantle. This early atmosphere would have been much denser than Earth's, implying higher pressure. Under these conditions, water vapor in the atmosphere could have condensed into an ocean, possibly even a global ocean. However, this ocean would have existed at high temperatures, similar to a pressure cooker. Over millions of years, this large body of water started to cool down, potentially creating the first opportunity for the emergence of life around 4.4 to 4.3 billion years ago. It is important to note that this is purely speculative and based on modeling. There is no direct proof of it. In any case, this early atmosphere would have lacked stability because as the planet kept cooling down, it would have escaped into space or become incorporated into the surface. After liquid water and high pressure, the atmosphere would have become thinner and thinner, and the planet increasingly cold. As a result, turning water into ice. The following 400 million years, from 4.1 to 3.7 billion years ago, new drastic changes. Bombardment by asteroids could have kept happening, like on Earth. In the southern hemisphere, the surface would date from this period, like on Earth. Mars probably has a liquid core made primarily of metal. Metals tend to converge to the center of planets due to their higher mass. The core is covered by a mantle and a much thinner solid crust. On average, this crust today would be around 50 kilometers thick, compared to 40 kilometers on Earth. Once again, this is an estimate that looks possible, even reasonable. However, contrary to Earth, it could not be proven directly and by multiple methods. But at the time, 4 billion years ago, this crust was much thinner, and the planet had a period of intense volcanic activity. Great volcanoes appeared. After our landing, we will pay a visit to one of them, Olympus Mons. The fracturing of the surface made a large rift valley system appear as a result of this volcanic activity, pulling gases and ashes into the atmosphere. the planet would have stopped cooling down because the thicker blanket of gases trapped more solar heat, causing a greenhouse effect. At this point, clouds probably developed, and with them, precipitations running to the ground. This could explain the valleys that were possibly dug by running water billions of years ago through erosion. At the time, there could have been also lakes forming in the basins and craters, maybe even an ocean covering the north of the planet. A clue that points to such a scenario, with the existence of an ocean or at least running water, is the analysis of rocks on the surface by rovers. They indicate the presence of clay minerals that typically form by prolonged exposure to groundwater. During this second period, another window for the possible emergence of life, the second one theoretically opened. There was liquid water, an atmosphere, and also maybe a magnetic field around the planet, like on Earth. The inside would have been in motion, like on Earth, creating a magnetic dynamo that would have shielded the planet from radiation. In theory, this would make several of the conditions that allowed the appearance of life on Earth possibly present on Mars at the time. But again, these conditions didn't last more than a few dozen million years. Mars is a smaller planet than Earth, and as a result, it cooled down faster. Therefore, the magnetic dynamo would have shut down, causing the magnetic field to disappear. However, more concerning for the possibility of life on the surface is the fact that atmospheric conditions continued to change due to Mars' smaller mass compared to Earth. Without a magnetic field, Mars kept losing its atmosphere, which dissipated into space over millions of years. Eventually, what remains of the atmosphere started to cool down again. And with the accumulation of gases like sulfur pulled by volcanoes, rains would have become increasingly acidic over a period of 800 million years, until about 3.6 billion years ago. Once again, this hypothesis is supported by the analysis of soils that were apparently altered by acidic groundwater. As the temperature went down, much of the water would have frozen, possibly under the surface bombardments by asteroids that had become less and less frequent over hundreds of millions of years. They almost came to a halt, like on Earth. At the same time, in the rest of the solar system, maybe eventually, there were still asteroid impacts that melted huge quantities of surface ice and caused catastrophic floods. However, these floods could only be short-lived because the water was reabsorbed into the ground and frozen again. After 1.5 billion years of catastrophic reverses in its appearance and atmosphere, Mars then entered a period of relative stability that continues to this day. During this stability, in the sense that there were no more large-scale geological changes or climatic changes, the surface of Mars became dry, bearing little resemblance to its previous atmospheres. The new atmosphere has become so thin that there is very little pressure at the surface, so much so that water vaporizes instantly upon reaching the surface, Therefore, there can no longer be liquid water. Over 3 billion years, there was still erosion, with powerful winds occasionally. Volcanoes appeared and modified the surface, like they do on Earth. But there doesn't seem to be plate tectonics like on Earth. The face of Mars may not have changed radically for a long time. Now, seen from space, it has this red color that comes from oxidation of iron. It is rust that gives Mars its name of the red planet. The poles remain covered in ice, and the size of this ice continent at the poles probably varies over very long periods, depending on the distance from Mars to the Sun. I will tell you more about the conditions at the surface, but it is now time to land, because we have reached our destination. We made this journey quickly, but for astronauts it will take months. Astronauts have already spent extended periods of time in space, including more than necessary to reach Mars. But it was in space stations that remained on the low orbit veranda. The psychological burden of knowing you are traveling further and further away from your planet in a potentially dangerous adventure and in an environment where only technology can keep you alive cannot be overlooked. This probably recreates the experience of the explorers who left Europe by sea in the 15th and 16th centuries, with their crews at the mercy of unpredictable oceans for months. There were situations of mutiny or despair. Now, this human factor can certainly be overcome by selecting highly trained astronauts and ensuring their group dynamic works for the mission. However, the psychological and social dimensions of such a journey bring challenges that cannot be fully eliminated. Additionally, there are biological and physical difficulties. Human bodies had not evolved for life in space, especially in zero-gravity environment. It is not just the loss of bone or muscle when we don't need to compensate for gravity for an extended period of time. There are other aspects that affect metabolism and the way our body heals. For example, it would be more difficult to treat a fracture without gravity. And this is something astronauts would need to pay attention to, as they could not afford to hurt themselves. But the biggest medical issue in space is certainly radiation. On Earth, we are shielded from radiation by our magnetic field and the atmosphere. The radiations we talk about here are streams of tiny particles, bits of atoms or energy that exist in space or come from the sun. The sun ejects them constantly in every direction, and they travel through the solar system. This is a big problem for extended stays in space because it is hard to fully shield against them, including inside spaceships or stations. One day spent in the International Space Station, for example, is the equivalent to roughly 10 sessions of chest x-rays. If it is for a day or two, there are no measurable consequences. But when it is for months, the damage to the DNA, eyes, and the immune system can become concerning. And it is more than enough to significantly increase the risk of cancer. This is far from being the worst place in space. It is on a low orbit and still within the Earth's magnetic field. So, traveling further in space will imply higher doses of radiation. And even more insidious effect of radiation exposure is that it may affect cognitive function over time, making astronauts less able to respond to enforcing circumstances or stressful situations. So, what can be done to minimize the problem of radiation? There are vests in development made of materials that are efficient at blocking free particles, like proteins. For example, vests made of polyethylene. Polyethylene is easy to make. It is a plastic. We use it all the time, and it is the material used for bottled water. There are radiation sensing instruments that could alert astronauts when they pass through a place where radiation is more intense, and they can move to a part of the craft where there is better shielding. Metals that make the hulls of spacecraft are not good at stopping radiation. But other materials apart from polyethylene, for example hydrogen, work well. It would be possible to integrate hydrogen-rich materials into the spacecraft's structure, or maybe just line the walls with water tanks. Now, these options also raise issues of weight, because all this has to be sent into space. Another solution being explored by scientists, and it sounds a lot like science fiction, is to give the craft its own electromagnetic field generated by a device on board the craft. It is possible for the long term, and it creates other problems like the energy necessary to make it work constantly. However, that would be an ideal long-term solution to the problems of radiation for space travel. Because until such a solution is found, longer haul space travel with astronauts will be hard and a direct threat to their health. One day in space outside the magnetic field of the Earth is equivalent to about 700 days on Earth when it comes to the dose of radiation received. It's almost like 2 years in a single day. In other terms, in 1 month in space outside the Earth's magnetic field, astronauts receive almost the equivalent of a lifetime of radiation on Earth if they are not protected. At this point, the issue of shielding against radiation is one of the biggest stakes for scientists who work on future manned missions to Mars or beyond that. We have now reached the proximity of Mars, and the first leg of our trip is done. Sometimes there are storms of dust on the planet that can reach global dimensions and completely hide the ground. This is one of the difficulties of the harsh environment we will find at the surface, but not today. Through the very thin atmosphere of the planet, we can directly see the ground and its variety of plains and craters, mainly in the southern hemisphere. We see mountains and rifts, all in various shades of red to brown, except for the white caps of ice at the poles. These caps are primarily water ice, but not only. They also contain frozen carbon dioxide. Like Earth, Mars has seasons because the planet rotates on an axis that is not perfectly perpendicular to its orbit. This means it does not always present the same side to the sun. when it is summer for one hemisphere or pole, that particular area receives direct sunlight. Meanwhile, the other hemisphere or pole experiences winter and remains in darkness for a month. Without an atmosphere to regulate temperatures, like on our planet, the dark pole becomes extremely cold, causing carbon dioxide in the atmosphere to freeze and fall to the ground. This results in a layer of carbon dioxide ice covering the dark pole. However, when summer arrives, sunlight causes carbon dioxide to sublime. That is, it instantaneously converts it from a solid to a gas. Carbon dioxide liberated as gas brings dust with it in the atmosphere, and clouds form, clouds that look like cirrus clouds on Earth, until the next change of season when carbon dioxide freezes again and falls back to the ground. We will keep exploring the surface, but now let's land. We will do it probably like the first human missions will land in a rocket, so that we would be able to take off at the end of the mission and return to the spacecraft left in orbit around the planet and start the trip back to Earth. A dozen small spacecraft have already landed successfully on Mars since the 1970s. There was a Mars 3 sent by the Soviet space program and Viking 1 and 2 by NASA. Then there was a long period when funding issues and other priorities put missions to Mars on hold. They resumed 20 years later in the 1990s with the appearance of rovers like Sojourner, Opportunity, Curiosity, and more recently, Perseverance, which landed in February 2021. Because of these missions that have collected samples, sent images from the ground, and the cartography made by probes in orbit, our knowledge of Mars has increased. It has improved dramatically in the past 40 or 50 years. Clearly, between these successful missions and the various long-term projects or manned missions from public and private agents that exist at the moment, Mars is a hot topic in the world of astronautics. A human mission is unlikely to take place this decade, but the next? Why not? This raises questions about whether it is worth it and how much it would cost. Apart from the risks of failure and the huge complexity, an obvious limiting factor is the cost. It is estimated to be roughly $500 billion. This is a lot, or not that much, depending on how you look at it. If you compare it to the world's economy, $500 billion is not that much. The world's GDP, the gross domestic product, is 104 trillion, so $500 billion would be 0.6 of 1 year of the world's economy. In other terms, it is equivalent to less than 2 days of economic activity on Earth. As a species, the perspective to try and go to another planet for the first time ever for the equivalent of 2 days of work doesn't seem like much. It can also be argued that this spending is also an investment for a part. This is the kind of project that needs research in materials, processes, fuels, and equipment of all sorts that could have other beneficial uses. However, this amount is well above the budget of any space agency or private investor, and it would certainly not be profitable financially. There are resources that could be exploited on Mars by a human community living there, such as water, metals, and maybe many other materials to be discovered, but there is probably no treasure to find. It would be for the sake of knowledge, for science, for the challenge itself, or the perspective to one day establishing a permanent human presence on Mars. It has been argued that this last point makes sense as a species for humankind. A presence on different planets strongly reduces the risk of extinction. If we wish to consider this a goal, because, apart from that, there are plenty of places on Earth that are currently unpopulated by humans, and that would be much easier and cheaper to colonize, like the poles, Arctic regions, deserts, or even the bottom of the seas. Each is inhospitable, but they are still way more welcoming than Mars for us. Even in the terrible cold and lack of vegetation of the Antarctic, for example, where the only human presence is on bases, at least there is air to breathe. There is pressure, so you can go without a pressurized suit. And the temperature is actually almost pleasant if you compare it to Mars. On Mars, the atmosphere is too thin to retain heat at night, and it is further away from the sun than Earth. The average temperature is minus 60 degrees Celsius, which is minus 80 degrees Fahrenheit. At best, the temperature near the equator during the day can rise up to 20 degrees Celsius, which is 70 degrees Fahrenheit. It doesn't sound too bad, but in the same location, the temperature at night will drop to minus 73 degrees Celsius, minus 100 degrees Fahrenheit. There is no place on Earth where the temperature varies by 100 degrees in a single day. In addition, the atmosphere on Mars is 100 times less dense and contains 95% carbon dioxide. So there is nothing to breathe for us. The problem of radiation and the dust storms can rage for weeks. Will make for a harsh environment. Any human community would face a precarious situation, relying solely on their equipment. They would probably need to find shelter underground or under anti-radiation domes. Additionally, they would desperately need to find water for extracting oxygen and irrigation for production. The production of energy, likely through solar panels, would also be risky if the sun is obscured by dust for an extended period. Pressurizing the living space would be necessary. All these factors carry significant risk, leaving no room for failure. Now, with the same amount of funding, it would be much easier to create an entire underground or underwater city on Earth that could exist and function completely separate from the rest of the world. Doesn't sound useful, and no one is going to invest in this. But if the argument in favor of establishing bases on Mars is to gain living space or protect humanity from extinction, it doesn't really work that well considering it could be done on Earth. But still, the challenge is fascinating. I think and I hope a human mission to Mars will one day leave Earth and succeed. One of the interesting questions it could answer would be the presence of traces of life on the planet. even if it is long extinct or dormant. If life appeared at some point on another planet in the solar system, then it would strongly suggest that the conditions that allow the existence of life are not that extraordinary. That would be a powerful argument in favor of the existence of life in multiple locations, multiple places in our galaxy. But having a base and a few scientists seems absolutely impossible, however difficult it is in the not so distant future. Now, it is not forbidden to dream, and for a longer time, the concept that has circulated since the 20th century is the idea of transforming Mars or other planets to make them more similar to Earth, inhabitable by humans and Earth-like life. As you know, this is called terraforming. What is terraforming? And is it just a dream or something that could happen for real? The concept appeared in science fiction in the 1940s. It is not that recent. The first notable scientific article about it was written by an astronomer named Carl Sagan in 1961. In this article, he proposed a theoretical way of transforming the planet Venus to make it habitable. At the time, it was known that Venus had a very dense atmosphere that created a powerful greenhouse effect, keeping surface temperatures at unbearable levels, hundreds of degrees. The composition of the atmosphere was roughly known. It had water, nitrogen, and carbon dioxide. So he proposed the idea of seeding this atmosphere with algae. It is so dense that algae would have stayed in suspension. They wouldn't fall to the ground and be incinerated. Algae would have converted the components of the atmosphere into organic compounds by feeding on them, especially carbon dioxide. This would have progressively removed carbon dioxide from the atmosphere and reduced the greenhouse effect until temperatures dropped to more comfortable levels, and the carbon would have remained captive in a blanket of matter that would have fallen to the surface. The oxygen would have to rise to make the air breathable. That was clever, but later discoveries showed that it couldn't work because the clouds of Venus are very rich in sulfuric acid that would have destroyed algae. And another problem, even more insurmountable, was that the atmosphere was just too dense. Algae might break carbon dioxide into carbon and oxygen, but oxygen would have stayed high, whereas pure carbon would have fallen to the surface, been incinerated, and through combustion returned to the atmosphere as a gas. Sagan also proposed a terraforming project in Mars in the 1970s, and because it is certainly the planet most similar to Earth in the solar system, the concept of terraforming Mars has persisted for decades. As we saw earlier, it is not impossible that Mars had an Earth-like environment in its history long ago, with a thicker atmosphere and abundant water, possibly liquid water. If the mechanisms that caused this atmosphere change occurred, they could potentially be reversed. I previously mentioned the likely reasons that caused Mars to lose most of its atmosphere. One reason is the absence of a magnetic field, which allows solar wind to carry the atmosphere away. Additionally, Mars has lower gravity compared to Earth. At the surface of Mars, an object weighing 100 pounds on Earth would only weigh 38 pounds. As a result, astronauts walking on the surface would not be able to generate as much force as on the Moon, but they would feel lighter compared to Earth. Furthermore, the lower gravity means that the atmosphere is less tightly bound to the planet compared to more massive planets. And finally, the last reason for the loss of this atmosphere is that when there is carbon dioxide in an atmosphere and water is present, it tends to react with rocks at the surface to form carbonates, which are solid salts. So, this tends to draw the atmosphere off and bind it to the surface. This happens on Earth, but due to volcanic activity that ejects new gases into the atmosphere, there is a kind of balance, and the Earth's atmosphere doesn't get eroded by its absorption into the surface. So, between these various effects, Mars's atmosphere was probably in the past carried away into space and absorbed by the planet itself. These problems are due to the mass of Mars, the lack of enough volcanic activity, and the absence of a planetary magnetic field. These problems cannot go away easily. This is what Mars is, and for these reasons it looks complicated to give it an Earth-like atmosphere, because even assuming it could be done technically and financially, this atmosphere would be unstable and would need constant maintenance and constant readjustments to stay in place. It would have to be replaced artificially, as it tends to get thinner without intervention. There are other technical problems. In order to be habitable, this atmosphere would have to be heated. Mars receives less light than Earth from the Sun because of the distance. The light level is about 60% of Earth's only. So if an atmosphere with the same composition and density as Earth were created, with the same greenhouse effect that retains heat, it would still be insufficient to raise the temperatures above 0 degrees Celsius. And water would stay frozen instead of becoming liquid. And then, even if all of this could be overcome, the soil is toxic for us. It contains a lot of chlorine, too much to make it suitable for agriculture. It would also have to be chemically modified. All of these problems, and there are others, actually have solutions that are technically possible and often within our technological reach. However, in practice, it clearly looks undoable for the moment. At the scale of an entire planet, we just don't have enough energy and the possibility to send the huge equipment necessary to Mars. But let's imagine we tried. What could be the methods employed to terraform Mars? The starting point would have to be to generate a greenhouse effect that is mostly absent at the moment by injecting gases into the atmosphere. These gases would trap solar heat near the surface and help start the process of global heating that could one day make the water at the poles and underground melt. They would also increase pressure and make it more bearable for humans. At the moment, the pressure is just 1% of Earth's pressure, so a pressurized suit is absolutely necessary. However, if this pressure reached just 25 or 30% of Earth, it would already be possible to go out without a suit. Just an oxygen mask would be sufficient. There are compounds with a significant greenhouse effect, such as ammonia and hydrocarbons, that are abundant in the solar system and could be imported to Mars. We know where to find them, for example, on the moons of Jupiter. However, these compounds are relatively light, and it could be hard, especially at the beginning, to make them stay around the planet. Another option would be to release gases with very powerful greenhouse effects into the atmosphere, such as fluorine compounds. These include the famous CFCs that became known for attacking the ozone layer on Earth. But they are also very powerful greenhouse gases. In fact, they are thousands of times more powerful than carbon dioxide. Fluorine is present in the Mars crust in higher quantities than on Earth, as far as we know. So, an idea could be to manufacture these compounds from the materials present in the soil and release them into the atmosphere. Alternatively, send rockets with payloads of compressed CFCs. When it comes to warming the planet, a proposed solution would be to use orbital mirrors to redirect more sunlight to the surface. They could also be targeted at the poles and their layers of solid carbon dioxide to try and sublimate it and help kickstart the greenhouse effect. Another necessity would be to oxygenate this atmosphere if it becomes dense and hard enough. Science fiction often uses the idea of seeding the planet with algae or vegetation. In general, this could help, but it is not such a good solution because the net production of oxygen by terrestrial plants is quite small, even on Earth. Plants reabsorb oxygen at night, and in fact, on Earth, more than 2/3 of oxygen is produced, generated by the oceans. Liquid water would probably be necessary to fill the atmosphere with oxygen and support vegetable life, capable of initially withstanding the extreme conditions of low pressure and cold. Alternatively, water could be introduced, or an alternate solution could be the creation of oxygen from water in industrial plants. As you know, oxygen is the main component of water along with hydrogen. Finally, even if all of this could be sorted out, there will always be the problem of Mars and its ability to retain its atmosphere. As a solution, the idea of creating an artificial magnetic field has been proposed, which in theory could be achieved with superconducting rings built around the planet, through which electric current would constantly circulate. At the scale of a planet, this is, of course, very theoretical. So, as you can see, the terraforming of Mars is not for tomorrow, or even the day after tomorrow. But at the end of the day, technical solutions are not completely out of reach. It could become a viable project in the future if mankind had considerable sources of cheap energy at its disposal, far more than today. However, with equipment that could harvest the sun's energy or generate it through fusion, it is not completely unthinkable in several generations. Before we leave Mars, I told you we would visit a volcano. Mars may be smaller than Earth, but it is home to one of the largest and tallest mountains known in the solar system, Olympus Mons. Olympus is an enormous shield volcano, which means it has grown a very wide base made of lava. It has ejected throughout its history. Olympus Mons has a surface as big as Italy or Great Britain, and its peak reaches 26 kilometers high, or 16 miles. That is more than twice the height of Mount Everest. It is believed that such a large volcano could appear because of the lack of plate tectonics on Mars. On Earth, a lot of the energy and pressure in the crust is released in rifts between plates, and volcanoes are not eternal. They are parts of plates that move and may disappear in the very, very long term. But when this mechanism doesn't exist, the volcano can stay in place and keep releasing lava for hundreds of millions of years. This is probably why and how Olympus Mons could reach such a size. And this is interesting because if lava keeps nearing the surface on Mars and assuming there are pockets of water trapped underground, then in some particular locations, there may be liquid water beneath the surface, water heated by a geothermal source. There are so many other interesting things to say about Mars. It also has satellites. We are at an exciting moment historically when it comes to space exploration. After the initial exploits of going to the moon and sending probes to the various corners of the solar system in the 1960s, space exploration has slowed down in the following decades. But there is a resurgence happening at the moment with different actors. There is NASA, private companies, China, the ESA, Russia, Japan. Many of the missions and projects are planned and collaborative. Maybe not with China, but in general they are. It still may seem painfully slow when you follow space news on a daily basis. These projects take years. But on a historical scale, it seems we are returning to the kind of excitement there used to be in the 1950s and 1960s, and I am happy about it. We are going to space again tonight for a new cruise in the solar system. Our destination is the system formed by Jupiter and its numerous satellites. We will visit several of them, not just the 4 main moons of Jupiter, which are very different from one another, but also smaller satellites. We will discover what the splendid features of the solar system are thought to be made of, how it interacts with other bodies, and what could be found inside and on the surface of its moons, where we will spend most of this journey. As you know, Jupiter is the largest planet in the solar system and is visible to the naked eye on many nights. The first planets from the Sun in our solar system are rocky: Mercury, Venus, Earth, and Mars. Beyond the orbit of Mars begins the realm of gas and ice giants, planets that do not have a well-defined hard surface, but are giant balls of gas.
becoming denser and denser as you approach their core. It is believed that underneath all these layers of increasingly hot gases, they have a solid core where metal dominates. These include Jupiter, Saturn, Uranus, and Neptune. However, rocky bodies can still be found beyond Mars, and there are many of them. Some float in a region called the asteroid belt. Between the orbits of Mars and Jupiter, including fairly large ones like Ceres or Vesta, but are not large enough to be classified as planets. Nevertheless, they follow their own orbit around the Sun. Beyond Neptune, there is also an even larger asteroid belt, the Kuiper Belt, that includes Pluto and Eris. In between these two asteroid belts, in the region of the gas and ice giants, there are many, many rocky and solid bodies of all sizes that had been captured and turned into satellites by these gas giants. Jupiter has dozens of satellites. Some are called moons because they are larger and, due to their size, tend to adopt a poor spherical shape. Others are smaller, akin to asteroids. Sometimes a few miles across or less, all the way down to small rocks and dust. Saturn has so many small objects in its orbit that they are so brilliant that they form visible rings. Jupiter also has rings, but they are not as large and are less dense, which is why they are more discreet. Along our cruise, we will land on several of the larger satellites, including the 4 main ones that are called the Galilean moons of Jupiter. They were observed for the first time with a rudimentary telescope by the Italian astronomer Galileo in the 17th century. But first, let's go to Jupiter. In our last cruise to Mars, I told you about the distance and how an itinerary could be decided based on orbits and the distance from Earth to Mars. Because the distances between planets are constantly changing depending on their own movement along their orbits, sometimes they can be aligned on the same side of the Sun, in which case they are closer. Or they can be on either side of the Sun, and in that case, the distance is much more. The same applies to travel from Earth to Jupiter. When the two planets are at their closest point, the distance is 365 million miles, almost 600 million kilometers. At its farthest, it is almost twice as much. Now, to get a sense of distance inside our solar system, let's bear in mind that Earth is actually much closer to the Sun than it is to Jupiter. The distance between Earth and the Sun is about 93 million miles, or 150 million kilometers. And to express astronomical distances in a simpler way, a unit, the astronomical unit, was defined as 1 astronomical unit is equivalent to the distance between our planet and the Sun. So, by definition, Earth is 1 astronomical unit away from the star, and Jupiter is 5 times farther, precisely 5.2 astronomical units, meaning that the planet and its moons receive less solar energy, and also that light from the Sun reaches them later than Earth. The sunlight needs only 8 minutes to reach Earth, but needs 43 minutes to reach Jupiter. Being farther from our star, Jupiter also has a much longer orbit than Earth, and it is slower on its orbit. Actually, the farther the planets are from the Sun, the slower they tend to be in their orbits. This is an effect of gravitation. The fastest planet in the solar system is also the closest to the Sun, Mercury, and it travels in space at almost 50 kilometers per second. That's the equivalent of more than 100,000 miles per hour. Earth travels close to 30 kilometers per second, or 18 miles per second. Jupiter is significantly slower, only 8 miles per second, or 13 kilometers per second. And so, between the longer distance to complete one revolution around the Sun, plus the slowest speed, Jupiter needs a lot more time to complete a full revolution and orbital journey around the Sun. It needs about 12 of our years. The one characteristic that makes Jupiter stand out in the solar system is obviously its large size. It is still a very small body compared to the Sun, less than 1,000th of the Sun's mass. But it is much bigger than any other planet, and even bigger than all the other planets of the solar system combined. Its mass is 2.5 times the mass of all other planets together. We will pay more attention to Jupiter later, including its composition and formation history. But for now, we are approaching its periphery, and it is time to take a look at its larger moons. As I mentioned before, there are 4 of them: Io, Europa, Ganymede, and Callisto. They are all very different from one another, and we are going to make a stop on each one. These 4 moons are the Galilean moons, as we said earlier, because they were first observed 4 centuries ago by Galileo Galilei. At the time, they were the first objects found to orbit a planet other than Earth, and their discovery was a big deal because it changed views on the nature and the shape of the cosmos. Jupiter has always been well known since the dawn of human times, because it is visible in the night sky. After the Sun and Venus, it is the brightest object, but its satellites are way too small to be visible to the naked eye, so only the use of a rudimentary telescope made the observation possible. We will explore their history, their orbits, and how these orbits are in resonance with each other. But for now, let's approach the first one, Io. Io is the closest to Jupiter of the 4, the innermost and the 3rd largest of the Galilean moons. It is slightly larger than our moon, and it is a very dense body, the densest of any moon in our solar system. It also stands out for its extreme volcanic activity. There are more than 400 active volcanoes on its surface, some of which produce plumes of sulfur that climb as high as 300 miles, or about 500 kilometers. This makes the surface of Io constantly ravaged by eruptions and clouds of gas released by the volcanoes. To us, it may look almost like the representation of hell. So, why is Io so geologically active? It's because of the presence of Jupiter and its moons, but especially the mass of Jupiter, which causes a phenomenon called tidal heating. What is it? You know that rocky planets and moons in the solar system are very hot inside. Their crust at the surface solidified because it became cooler over time. And with this cooling process over millions and millions of years, the crust tends to become thicker. But there is still intense heat inside that remains trapped because of mainly two phenomena. First, there is the creation of these bodies when a lot of smaller asteroids and dust collided to form them. These collisions generate a lot of energy, a lot of heat, that dissipates very slowly because it is accumulated inside under the crust. Then there is a second and more important phenomenon that happens inside planets: radioactive decay. Unstable large atoms like uranium and a few others undergo fission. They suddenly reorganize their particles into smaller atoms. In the process, they liberate energy and free particles that do not get incorporated into the new atoms. This fission of unstable atoms tends to make them disappear over time, taking hundreds of millions of years for some of them, and there are fewer and fewer, but they still maintain a residual presence. Their decay, this radioactive decay, because it liberates radiation, is a natural phenomenon and keeps heating rocky planets and satellites from within. This radioactive decay also happens inside the moon, our moon. And there is most probably the same mechanism inside Io. But in the case of this body, a much bigger contributor to its internal heating is the mass of Jupiter nearby and the gravitational forces that result from it. As Jupiter is very massive, the side of Io that is closer to the planet experiences a slight larger gravitational pull than the opposite side. And due to the presence of other moons around that influence its orbit, the orbit of Io is not perfectly circular. It is elliptical. Depending on its position, the moon can be closer or farther from Jupiter. This means that as the moon is in motion, it is subject to different intensities of gravitational pull, and this force causes distortion of Io's shape, as if you had an orange in your hand and you would squeeze it, pressing in different parts. It's not going to destroy it, but it is going to flex its interior. This happens to Io, and at the scale of a rocky body like this one, it means constant friction inside the planet, which generates heat. And this is tidal heating. The gravitational pull of a large body that is strong enough to distort its satellite, as a satellite follows an elliptical orbit and moves from being closer to farther constantly. More than any moon in the solar system, this heats the inside of Io due to friction, and this is what drives its intense volcanic activity. There is a lot of energy waiting to be released, and the constant flexing of the moon makes its surface prone to moving and breaking. Apart from volcanoes, more than 100 mountains have been identified, uplifted by compression of the crust. Io may be much smaller than Earth, about the size of the moon, but it has mountains higher than Mount Everest, and between these spectacular mountains there are rocky plains where, again, volcanism influences the moon, because lava is constantly released. Io has a relatively young surface that gets renewed with the new material coming from inside the moon. Through telescopes and cameras, Io appears in shades of yellow, white, black, red, and even green, corresponding to different types of sulfur. All surfaces on moons and planets tend to have visible craters, the remains of asteroid impacts, but Io doesn't. This is because the surface flows of lava, which can sometimes be several hundred miles long, constantly renew its surface and erase traces of impacts. There is a very tenuous atmosphere on the moon. First, because it is not massive enough to retain a thick atmosphere, and second, because Jupiter is close, as we said, and tends to steal gases from Io due to its gravitational pull. It is estimated that the atmosphere loses a ton of matter per second due to this. This is not that much on such a scale, and the faint atmosphere gets renewed by gases released by the volcanoes, mainly sulfur dioxide. As soon as they are released by the volcanoes, these gases tend to freeze due to the intense cold. The inside may be very hot, but Io is much farther away from the sun than we are. There is no atmosphere to retain heat, and when the moon passes in the shadow of Jupiter, it does not receive any solar energy at all. But when Io is exposed to the sun, a superficial layer of this sulfur dioxide sublimates, which means that it returns instantly to a gaseous state. And this is what maintains a bit of atmosphere. There would be much more to say about Io. But let's move to a second moon, one that also has exciting features, Europa. Europa presents a few cracks and streaks on its surface, but it has the smoothest surface of any known solid body in the solar system. There are very few craters or mountains. It is the smallest of the 4 Galilean moons, and it is slightly smaller than the Earth's moon. Why the smooth surface, and what is Europa made of? Its density suggests that overall its composition is similar to terrestrial planets of the solar system. Primarily, it is made of silicate rocks, that is to say, large quantities of silicon and oxygen, and its core is likely rich in metal, especially iron. But the smooth surface and other observations strongly suggests that the outer layer of the moon is made of water. Approximately 60 miles, that is 100 kilometers thick. Thus, the surface of Europa would essentially consist of frozen water ice. The question arises, if the temperatures are higher beneath this layer of ice, could there be an ocean of liquid water underneath? However, first we must understand the dynamics of this solid surface, as it features many dark streaks or lines that are visible from space. The most likely explanation is that there have been, and continue to be, eruptions of ice between plates. This ice would be warmer and erupt, causing the crust to spread open and expose the warmer layers beneath. In a sense, this phenomenon is reminiscent of the oceanic ridges on Earth that occur between plates, even though, in this case, the environment and materials involved are completely different. This is compatible with the existence of a subsurface ocean. If the ice between the crust is warmer, there may be a point where the temperature is high enough for water to become liquid. What could heat this ocean? High temperatures from the inner layers of the moon. And here, like for Io, we see the phenomenon of tidal heating that we have just discussed, which may contribute to warming the water. Surface temperatures are extremely cold, with equatorial temperatures around minus 160 degrees Celsius, which is minus 260 degrees Fahrenheit. This extreme cold is due in part to the almost complete lack of atmosphere and the fact that Europa receives less sunlight than Earth. At the poles, the temperature plunges to minus 220 degrees Celsius, and Europa also regularly passes into the shadow of Jupiter for several hours. Europa takes 3.5 days to complete its revolution around Jupiter, so for several consecutive hours it is plunged into complete darkness and no longer receives direct sunlight. At these times, the surface temperature at the poles drops to a level not far from absolute zero. In any case, the ice crust is thick, at least several miles or kilometers. However, there is an ongoing debate about the exact thickness of this crust. This is important because if it is relatively thin, there could be exchanges between the liquid ocean and the surface from time to time, for example, when these streaks form, or perhaps when an asteroid hits the moon and breaks the crust. If the ice crust is dozens of kilometers thick, the hypothetical liquid ocean and the surface would be completely separated. But in any case, the existence of liquid water on Europa is likely, and there could possibly be a significant amount of water, especially if the water layer is about 100 kilometers thick, which is the dominant theory at the moment. And even if half of it is solid ice, that would still mean a substantial amount of liquid water, which, by Earth standards, is absolutely enormous. So, if there exists a place with both water and heat emanating from the inner layers of the moon, then this raises the possibility of the existence of life on Europa. This is why, over the past few decades, this moon has been prominent among the moons of Jupiter. Following various discoveries about Europa itself, its composition, and analogous discoveries on Earth in the abyssal depths, we know that life can thrive in complete darkness, with food chains beginning with bacteria capable of withstanding very high pressure and temperature. These bacteria can feed on chemicals released by the Earth's crust, and then larger and more complex organisms feed on these bacteria. So it is conceivable that a familiar phenomenon exists thousands of kilometers under the extremely cold ice crust of Europa, in the darkness and the high pressure of its subsurface ocean. This discussion pertains purely to theoretical conditions for life that could be present on the moon. There has never been any proof of its existence. However, there are long-term projects for missions that could go to Europa to search for evidence of life. Nonetheless, even if life exists somewhere on Europa, doesn't mean its surface would be hospitable to humans at all. Apart from the cold, radiation levels are very intense. owing to the lack of atmosphere and the absence of a magnetic field akin to Earth's. Jupiter, being close, emits significant radiation. Therefore, any manned mission would have to be heavily shielded against radiation or be buried deep in the ice to find protection from this radiation. Now let's turn to the largest and the third one outward from Jupiter, which also presents a completely different environment, Ganymede. I mentioned that Europa requires 3.5 days to orbit Jupiter. Ganymede needs 7 days. Interestingly, there is an interaction between these 3 satellites, Io, Europa, and Ganymede, and the planet Jupiter. The 3 satellites are in orbital resonance. Their orbital periods are synchronized. Europa takes exactly twice as much time as Io to orbit Jupiter, and Ganymede takes twice as much time as Europe, which is exactly 4 times as much time as Io. They are in an orbital resonance of 1, 2, 4. What is this concept of orbital resonance, and why does it occur? As you know, all planets in the solar system orbit around the Sun, which has by far the largest mass of any object in our system. In fact, the Sun accounts for more than 99% of the matter in the entire system. But the Sun is not the only body that influences orbits. Even though they are smaller, planets also exert influence over each other. This depends on their masses and the distances between them. So it is correct to say that the Sun determines all orbits because it is by far the biggest factor. But if we delve a bit further into detail, saying it is 100% accurate is not entirely true. Other bodies, every body in fact, has a small influence on every other one. A large planet can distort the orbit of a smaller body and, eventually, modify it so much, revolution after revolution, that this object may be placed in another orbit or even expelled from the solar system. This has probably happened many times throughout the history of the solar system. This is a phenomenon that can greatly increase the influence between 2 bodies in space when they exert regular, periodic influence in each other. For comparison, think about when you are pushing a child on a swing. The swing has its own frequency, but even without touching the ground, the child can amplify the movement by pushing with their body. Because this pushing acts in periodic repetition, it has a cumulative effect on the motion. On a larger scale, this is what can happen between planets or moons orbiting a planet, and this phenomenon is called orbital resonance. Very often, this mutual influence is unstable. The 2 bodies exchange momentum, which progressively shifts their orbits to the point that the resonance disappears. However, under certain circumstances, a resonance system like this can become stable because it is self-correcting. The exchange of momentum between bodies keeps them in a stable resonance. This is the case, for example, between Neptune and Pluto, which are in resonance of 2 to 3. It means that when Neptune completes precisely 3 revolutions around the Sun, Pluto does exactly 2. The same kind of resonance formed between Io, Europa, and Ganymede in a ratio of 1 to 2 to 4. When Ganymede does 1 revolution around Jupiter, Europa does 2 and Io does 4. Another effect of momentum and gravitation that applies to Ganymede is that the moon is also tidally locked to Jupiter, meaning it always presents the same face to the planet. Most moons have this characteristic. They don't rotate on themselves, similar to our moon, where we always see the same face from the Earth. But now let's take a closer look at Ganymede itself. What stands out most about Ganymede? It is the largest moon in the solar system. Its diameter is only 40% of Earth's diameter, but it is larger than the planet Mercury, although not as massive, because Ganymede is made of lighter materials, lighter elements. Mercury contains a lot of metal, whereas it is estimated that Ganymede has a core of metal and rock, but is also half made of water in different states, including various types of ice. I'll come back to this, and perhaps among them there could be liquid water. So, as with Europa, there is speculation about the possibility of life in the oceans of Ganymede. It looks less likely or harder to prove for several reasons. First, because the outer layer of ice is much thicker than on Europa, making reaching the liquid parts very difficult, almost impossible at the moment. Additionally, it is uncertain whether the bottom of this subsurface ocean reaches the rocky mantle underneath. It is believed that there is another layer of ice, but not the same type we are familiar with on Earth. On Earth, we essentially know ordinary water ice, which forms under certain conditions of pressure and temperature, typically when the temperature drops below 0 degrees and at sea level pressure. But if the pressure is higher, a lower temperature is required for water to freeze. Now you know that ice is a crystalline form, meaning that water requires a highly ordered microscopic structure. Billions and billions of molecules become perfectly ordered, following a pattern. This almost never happens on Earth due to the conditions of temperature and pressure present on our planet. However, there are different possible crystalline forms, or patterns, that water may adopt. These different crystalline structures have been explored and studied in laboratories, showing that various types of ice may exist. Ordinary water ice is called Ice 1, and many other structural possibilities have been identified, such as Ice 2, 3, 4, Ice 5, and so on. It is believed that the inner layer of ice in Ganymede is Ice 3, which forms when liquid water is exposed to temperatures of -20 to -30 degrees Celsius and a pressure of 200 to 300 times the sea level pressure we live on Earth. On our planet, these conditions can only be replicated in a laboratory because, naturally, where there is enough pressure at the bottom of the oceans, the temperature is higher than that, and where the temperature is low enough, since -20 to -30 degrees Celsius is perfectly achievable in the winter in many parts of the world, there is not enough pressure because it is at the surface. So these conditions are not naturally met in our environment, but it seems they are in the depths of Ganymede's oceans. At its surface, Ganymede is primarily composed of water ice, but there are other elements that likely arrived as a result of impacts with smaller bodies. 1/3 of the surface is dark, covered in clays and organic compounds that are believed to be traces of impactors that collided with the moon. Contrary to Europa and Io, Ganymede's surface is quite ancient on average because there is not much geological activity to renew it. However, there are still grooves and ridges that are not completely explained at this point. Given the structure of the moon, these features could have appeared many hundreds of millions of years ago, when its surface was more active than it is now. Ganymede may have a lesser chance of harboring life than Europa, but when it comes to human presence and exploration, it may be a bit more welcoming. There is less radiation due to the longer distance from Jupiter, and also thanks to a degree of protection from a magnetic field that seems to be generated, like on Earth, by the dynamo effect of a rotating metallic core at the center of the moon. The level of radiation is still deadly, and the temperature and pressure are very hostile. But with adapted protections, it is not impossible to think of a human base one day on Ganymede. Out of the different moons of Jupiter, Ganymede presents a less challenging set of conditions than Io and Europa. But there is still something even better: Callisto. We still have a fourth Galilean moon to look at. Callisto is the fourth of them by distance to Jupiter, and thanks to this, it has the lowest radiation levels. However, there are other interesting features that distinguish it. I mentioned that the surface of Io and Europa were fairly young in astronomical terms, that is to say, still millions of years old. But in contrast, Callisto has the oldest solid surface in the entire solar system. It seems that since its formation, there have never been any kinds of subsurface processes, like volcanism or plate tectonics, that could have regenerated the surface. So it has never changed at all, except for impacts. Callisto has the most cratered surface in the solar system, completely covered in impact craters that have appeared over probably several billion years. So, why is Callisto so inactive geologically? It is believed that this is due to its formation history. Callisto would have formed very slowly from the accretion of smaller rocks, but not fast enough to reach a high temperature inside. As a result, the moon is not fully differentiated internally. What this means is that bodies of a certain size, planets or large moons, tend to have a structure in layers internally. The heavy elements converge toward the center, to the core, and various elements above it form layers that are fairly distinct in terms of chemical composition and conditions of temperature and pressure. This is the case for rocky planets like ours and the first 3 moons we just visited. The process of differentiation is never 100%, for example. There can be movements in the mantle of a planet that can cause small quantities of metals to go up and reach the surface. But still, large bodies acquire an organized overall structure, one that is differentiated. However, this process was very incomplete on Callisto, making it the largest body in the solar system that is not fully differentiated. The elements inside are mixed up. There are several layers made of rock and ice mixed together. Here again, the various conditions mean that the structure of ice differs, depending on how deep it is inside the moon. The crust is made of ice 1, the ordinary one on Earth, but inside it is believed there is also ice 5, 6, and 7, with different crystalline structures, and under tens of miles of icy crust, probably yet again another ocean of liquid water. That has been isolated from space for billions of years, since nothing ever happens on the surface of Callisto except for occasional impacts that do not reach beyond the icy crust. After the Earth, Moon, and Mars, Callisto is a possible target for manned missions one day, clearly not in the 2020s or 30s. It is way farther than Mars, and there is no specific project now. But if one day humans set foot on one of the moons of Jupiter, it is likely to be Callisto first. The low radiation level and the geological stability are advantages, and Callisto would be a good base station for further exploration of the solar system and remote exploration of Europa in the search of traces of life, for example. And until now, we have spoken about the 4 main moons of Jupiter. Then there are many more of smaller sizes that were discovered long after. You remember that Galileo observed these 4 moons in 1610. It took almost 3 centuries until the end of the 19th century to start discovering more and smaller moons. Today, at this point, 79 moons in total have been found and named. They are called moons when they are large enough, and there are also moonlets and dozens of smaller satellites. Together with the planet, they form a system called the Jovian system. We'll take a look at some of these smaller bodies and also at the rings of Jupiter. But before that, let's take a look at the planet itself. As you know, Jupiter is by far the largest and most massive planet in the system. It has 2.5 times the mass of all other planets combined. It is also probably the oldest planet in the system, the first to form according to current models of planetary formation. These are theories based on our knowledge of the history of the solar system and physics, not absolute certainties. But the dominant models right now suggest that Jupiter formed quite far from the Sun, beyond the limit called the snow line. This is the distance from an early star where it is sufficiently cold for volatile compounds like water to condense into solids. The origins of Jupiter would have started with a large solid core, one of rock and metal, that would still exist today at the center of the planet. Around this core, huge quantities of gas like hydrogen and helium would have aggregated, kept together by gravitation. After a few million years, which is short at this scale, the various other planets of the solar system were not formed yet, and the system was essentially a gigantic disk of gas and dust, with a newborn star at its center. So, rather quickly, Jupiter gained enough mass to absorb everything in its orbit, to clean it up, and reach a mass that was already 50 times the Earth's mass. Nowadays, after absorbing more gases and rocky bodies, Jupiter is more than 300 times as massive as Earth. But because it is less dense, being primarily made of gas, it has 1,300 times the volume of Earth. However, the fact that it is a gas planet doesn't mean that it's like a cloud that could be crossed easily. The more you move towards the center, towards the core, the denser and hotter the planet becomes. Due to the mass, temperatures, and pressure inside, Jupiter's reach levels that are way higher than at the center of the Earth. and the gravitational forces that keep the planet together are very powerful. Jupiter's composition is dominated by hydrogen, constituting about 3/4 of its mass and 90% of its volume. There is so much matter that the interior is strongly compressed. This compression generates heat, and in fact, Jupiter emits more heat by itself than it receives from the Sun. However massive Jupiter may be, it is still not enough to ignite the same reactions of fusion between hydrogen atoms that happen inside the Sun, which is why it didn't turn into a star. We know that there are systems where more than one star forms, even though this is not the most frequent case. If Jupiter had gained more mass, it could have turned into a second star alongside the Sun, but the planet stayed well short of that threshold. It is estimated that it would need to be 75 times more massive to ignite fusion. So because it is a gas planet, there is no solid surface to land on. As the planet begins as a cloud of low density and becomes increasingly dense, if we were to enter this giant gaseous sphere, we would reach a layer of liquid hydrogen, turned into liquid by the rising pressure, followed by another layer of so-called metallic hydrogen, another phase of hydrogen. This doesn't mean it turns into metal in the usual sense of the term, but under such conditions, hydrogen behaves like an electrical conductor, which is why it is called metallic hydrogen. Jupiter and also Saturn, which contain a lot of this metallic hydrogen, form due to their large masses that compress hydrogen. Visually, when we look at Jupiter, we see several bands or belts of color, different colors that are segregated all around the planet. There is also a giant spot. These bands move at different speeds and are made of clouds of ammonia that float in the upper layers of the atmosphere. Their movements cause strong turbulence. In its upper layers, Jupiter has powerful winds. The various bands have different circulation patterns. They move at different speeds, and their interactions create turbulence and even storms. This is what the Great Red Spot is believed to be: a vortex, a storm, that probably did not always exist but has become a stable feature of Jupiter's atmosphere. Given Jupiter's size, the red spot is bigger than Earth and rotates counterclockwise in the opposite direction to the band of clouds. The phase of fast growth is long over for Jupiter. There is no longer much matter to aggregate like in the early stages of the solar system, but the planet keeps attracting bodies like comets, which are captured by its gravitational pull and fall on it. Jupiter is estimated to receive about 200 times more asteroids and comet impacts than Earth. For a long time, it was believed that Jupiter played an important role in shielding rocky planets, including ours, from asteroid impacts. It was thought to have acted as a gravitational well located at the limit of the inner solar system, being the first and biggest of the giant planets. So Jupiter would have behaved like a vacuum cleaner for the system, but this view is now more disputed. Due to its mass, Jupiter could attract more asteroids and comets, drawing them from the Kuiper Belt, a large belt of asteroids that exists beyond Neptune. However, this debate is still open, and it is uncertain at this point whether Jupiter serves as such a shield for Earth. In any case, due to its mass and age, Jupiter has the largest number of large satellites of any planet in our system. It also has rings. These rings are not as obvious as Saturn's and were only discovered recently in 1979 when a space probe, Voyager 1, explored the Jovian system. These rings are not as large comparatively as Saturn's, and they are much less bright, which is why they weren't seen before. Saturn's rings contain a lot of ice that reflects light, whereas Jupiter's rings are primarily made of dust. In between or around these rings, there are dozens of moons. As I mentioned earlier, Jupiter has 79 moons total, so let's explore a few of them. The Jovian Moons, other than the four largest ones, began to be discovered in 1892. Being much smaller, they were harder to identify from Earth. Initially, they were given numbers such as Jupiter 5, 6, 7, and so forth. Jupiter 5, also known as Amalthea, is the fifth largest moon, and the last one to be discovered by direct visual observation. The subsequent moons were found by photographic or digital imaging, meaning they were seen on photographs of space using extended exposure time, which allows the capturing of objects that may not have been noticed otherwise. Like other smaller moons, Amalthea interacts with Jupiter's rings, which contain dust ejected from the surfaces of these moons. Amalthea isn't large enough to acquire a spherical shape, so it appears irregular. Its maximum length is about 160 miles or 250 kilometers. Placed near Earth, it would appear around the size of Massachusetts or Belgium. Amalthea is believed to have formed far from Jupiter due to its lightweight structure and content of water ice. In the early stages of Jupiter's formation, the planet emitted a lot of heat. Based on the moon's proximity to Jupiter, this moon would have entirely melted. So the prevailing theory is that Amalthea formed farther out in the solar system and was captured as a satellite afterward. Visually, the moon appears very red, possibly due to sulfur collected from Io, which could explain its glow, but this is uncertain. Amalthea orbits at only 180,000 kilometers from Jupiter, which is marginally more than the diameter of the planet itself. From the moon, Jupiter would look enormous, appearing 8 times bigger than our moon appears when viewed from Earth. When we watch Jupiter in the night sky, there is one moon even closer than Amalthea, Jupiter 16, also known as Metis. It is the innermost known moon of Jupiter, orbiting at only 130 kilometers, which is less than Jupiter's diameter. Metis is the fastest moving moon of all, orbiting at a speed of 30 kilometers or almost 20 miles per second. This moon is far too small to be spherical. Its maximal length is 60 kilometers with a width of 40, so it resembles a large asteroid. Metis resides right in the middle of one of Jupiter's rings, which is not a coincidence as dust from this moon generates the ring. When Metis experiences impacts with rocks, material can easily be ejected due to the moon's low gravity. In addition to Amalthea and Metis, there are 2 more moons, Adrastea and Thebe, that possess irregular shapes. Beyond these, there are 70 other, smaller moons that orbit considerably further away Jupiter. These celestial bodies likely had their own orbits around the Sun, much like asteroids from the asteroid belt, but were captured by Jupiter over time. These moons float in space, away from the rings, and are only a few miles across in some cases. Some of these remote moons follow a prograde orbit, moving in the same direction as Jupiter's rotation, while others are retrograde, moving in the opposite direction. More satellites are likely to be discovered in the future. Currently, more than 20 of these small, irregular satellites have not been named and have only been assigned numbers. Discoveries continued to be made as recently as 2020. More moon candidates were found orbiting far from the planet. The total population of moonlets could number in the hundreds, depending on the size criteria established. First, what is the distance we need to travel to reach Saturn? As I mentioned during our visit to other planets, the answer is that it depends. The distance depends on where Earth and Saturn are in their respective orbits. If they are positioned on opposite sides of the Sun, this distance is going to be larger compared to when they are aligned on the same side of the Sun. When they are at their closest distance, on the same side of the Sun, the gap between them is about 1.2 billion kilometers. That's 750 million miles, or about 7 astronomical units. An astronomical unit is the distance from Earth to the Sun, a practical unit to benchmark distances in the solar system. This offers an idea of how far Saturn is from the Sun in comparison with our planet. By definition, we are 1 astronomical unit away from the Sun, whereas Saturn lies nearly 10 times more distant, at 9.5 astronomical units, give or take. It's because the orbits are not perfect circles. They are slightly elliptical, shaped like an oval. Therefore, the distance to the Sun varies slightly over time, depending on the position the planets occupy in their orbit. In other terms, our planet, from Saturn's perspective, appears very close to the Sun. When Saturn is on the other side of the star, opposite us, the distance increases, but not dramatically. It expands to 11 astronomical units instead of 7 at its nearest point. If we were to travel at light speed, it would take us around 1 hour to reach Saturn. As we're now leaving Earth's orbit and beginning to accelerate, let's talk a bit about what we'll find when we do reach Saturn. As you probably know, Saturn is a gas giant, the second largest planet in the solar system after Jupiter. Gas planets, unlike rocky planets, do not have a solid surface. They are made of increasingly dense layers of gas. It is believed that at their centers, there is a solid rocky or metallic core around which the gas accumulated during their formation process. Gas planets are held together by gravity. The large mass at the core of these planets pulls in and retains the surrounding gas. A hypothesis suggests that these planets must reach a certain size. They cannot be as small as Earth or Mars because a higher mass is necessary to keep them in one place. However, it's possible that both gas and rocky planets have similar origins. They begin as a solid core that appears in the process of star system formation, in orbit around the star. These protoplanets grow by absorbing smaller objects in and around their orbits over millions of years, and may also increase in size by absorbing asteroids that travel the star system. This is thought to be how Earth and other rocky planets like Mars, Venus, and Mercury have formed. However, the orbits of Jupiter and Saturn, which are significantly farther from the Sun than the rocky planets we talked about before, may have had an abundance of hydrogen and to a lesser extent helium that was not absorbed by the Sun. These are the materials that would have been attracted and collected by the two planets, clearing their orbits and forming the various gas layers of these gas giants. I'm using the conditional form here because even though there's a broad consensus about the main aspects of the solar system's formation history, variations exist between the models. These models' theories are inherently difficult to prove. It's not as if we could recreate the experience. For instance, if you examine the solar system in isolation, it might appear as if rocky planets tend to be closer to the central star, as is the case for Mercury, Venus, Earth, and Mars. Further out, you'd find gas giants such as Jupiter and Saturn. And even farther out, ice giants like Uranus and Neptune. However, the examination of other star systems and the growing number of discovered exoplanets indicate that other types of planet placement are feasible. For example, we observe gas giants located nearer to their stars, referred to as hot Jupiters, because of their proximity to their stars. They may have formed far from their star and later shifted orbits, demonstrating that other constellations do not necessarily disprove the theory that gas giants typically form far from stars. This point illustrates that debates about the formation history of star systems and emergence of different kinds of planets remains ongoing. We will elaborate much more on Saturn itself shortly, but for now, let's enjoy the fact that we've considerably reduced the distance to the planet. With each passing moment, it becomes bigger and more imposing. We have surpassed the orbit of Jupiter, which marked the halfway point in our journey. Even though Saturn's mass is substantially less than Jupiter's, the size of the planet and its even larger rings is truly awe-inspiring. Saturn, while less massive than Jupiter by a significant margin, is almost as large in size. It contains 3 times less matter, meaning its mass is 1/3 of Jupiter's, so it is less dense. Why Saturn can maintain nearly the same size with less than 1/3 of Jupiter's mass is an interesting query we will explore later. But before we reach the planet itself and its dramatic rings, let's devote some time to exploring its fascinating moons. The moons of Saturn are equally interesting and could merit their own dedicated discussion. Although they may not be as famous as its rings, Saturn boasts more moons with confirmed orbits than any other planet in the solar system, a total of 146 moons. However, defining what qualifies as a moon raises certain questions. Technically, each block, or even each particle in the rings of Saturn, is a satellite of the planet. With billions and billions of such particles in the rings, we can't really consider them moons because of their small size and lack of independence. The moons I am referring to are distinct bodies, separate from the rings. They have been included in the count of 146 only when they can be repeatedly observed and their orbits identified. If we were to lower the threshold of what qualifies as a moon and accept smaller bodies, the number of moons could potentially number in the hundreds. But for tonight, we're going to pay a visit to some of the most prominent moons. On our list are Titan, which is the largest moon of Saturn and the second largest in the solar system; Rhea, the second largest moon of Saturn; Iapetus, the third largest; and Enceladus. Each of these moons has unique aspects waiting to be revealed. Let's begin by taking a look at Titan, the largest and most famous of these moons of Saturn. It is actually so large for a moon that only one is larger in the solar system, Ganymede, the moon of Jupiter. For comparison, the diameter of Titan is 40% of the diameter of Earth, which makes Titan significantly smaller than our planet. However, it is approximately 50% wider than our moon. For reference, our moon is the fifth largest in terms of diameter in the solar system. The top two are Ganymede and Titan, as mentioned. The third and fourth are two other moons of Jupiter, Callisto and Io. Coming in at sixth place, just after the Earth's moon, is another Jovian moon, Europa, with Jovian referring to Jupiter. Another element of comparison is that if Titan were not a satellite of Saturn, but orbited the Sun independently, it would be considered another rocky planet, as it is larger than Mercury. However, while it is larger, it is not as massive. Titan has only 40% of the mass of Mercury. Mercury is mostly composed of iron and dense rock, whereas a large portion of Titan consists of ice, which is far less dense than the materials we talked about. Despite its distance from Earth, Titan was discovered fairly early, around the mid-17th century, by a Dutch astronomer, Christian Huygens. This was relatively later in comparison to the moons of Jupiter, which had been discovered a few decades earlier by Galileo. Titan is about twice as far away, yet it is large for a moon and is relatively shiny, with a uniform yellowish atmosphere. This characteristic aided Huygens in detecting and studying it, much like the planet Venus. Titan reflects sunlight and is far enough away from Saturn to be differentiated from it with relatively rudimentary telescopes. Yet for 350 years, our knowledge of Titan remained elementary. Their surface was impossible to view, hidden beneath a thick and impenetrable atmosphere, resembling the situation of Venus. Our comprehension of this moon's surface and atmosphere has mainly been formed via discoveries made in the past few decades by probes, particularly in 2004, when the Cassini probe approached it. It is relatively uncommon for a moon to possess a dense atmosphere. This can only occur when the moon's size is large enough for its gravitational pull to retain the atmosphere. As we've noted, Titan is the second largest moon in the solar system. Additionally, over hundreds of millions or even billions of years, these moons must be able to preserve their atmosphere, as an atmosphere can be lost due to a collision with another body, or by passing too closely to a planet that could steal it, or it could be carried away by the solar wind, which is the flow of particles and radiations that come from the sun. These are extreme conditions, and perhaps for this reason, only two moons with a significant atmosphere are known in the system: Titan and Triton, a moon of Neptune. Both of these moons are relatively large and far from the sun, with different conditions that probably explain how they have managed to retain their atmospheres. Other moons generally have very faint atmospheres, not dense enough to be comparable to the kind of atmospheric conditions we are familiar with on Earth. However, Titan truly differs. Its atmosphere is very heavy and dense, so dense, in fact, that the surface pressure is higher than that on Earth. It is estimated to be close to 1.5 atmospheres, slightly higher, 50% higher than the atmospheric pressure we are accustomed to at sea level on Earth. This level of pressure would be like swimming a few feet underwater, an experience that would be perfectly bearable to human beings. While the atmospheric pressure might be livable, other conditions are not. The atmospheric composition is primarily nitrogen, accounting for 97% of it, along with methane and traces of hydrogen. Our own atmosphere is 70% nitrogen, but we also have 20% of oxygen that we can breathe. Titan's atmosphere doesn't have gaseous oxygen on its surface, meaning we couldn't breathe without a suit. Another major problem for human beings would be the temperature. Titan is nearly 10 times as far from the sun as Earth, and this produces only about 1% of the sunlight we receive. Not much sunlight at all. On top of that, 90% of it is absorbed by Titan's thick atmosphere, with only the remaining 10% reaching the surface. Now, because the atmosphere is thick, there also exists a greenhouse effect like that on Earth, helping to retain a bit of heat. Despite this, the temperature on Titan is frigid, measuring approximately 94 Kelvin, or 179 Celsius, a temperature at which water would instantly freeze. But without this greenhouse effect, it would be even colder. And yet, another problem that man could face on the surface is the constant darkness, with 1% of the light of night on Earth, and the thick atmosphere hiding the sun. You are plunged into near perpetual night. But let's say we have a suit with heating and oxygen mask and lighting. What would we see at the surface of Titan? An extraordinary landscape, actually. At the same time, it's completely alien chemically, but somewhat familiar in its geography. Titan is thought to have standing bodies of liquid on its surface, including rivers and lakes and seas. Except these bodies don't contain water because it would freeze, but rather liquid hydrocarbons like methane or ethane. Titan is believed to be the only place in the solar system, except Earth, to have such liquid bodies with a cycle of evaporation, clouds and rain like on Earth, except it's not water but hydrocarbons. Apart from the cycle of precipitation, mountains and volcanoes have been observed, but these are not Earth-like volcanoes. They are cryovolcanoes. A cryovolcano erupts volatile materials and gases, such as ammonia, water, or hydrocarbons. All these materials that astronomers call ices. It's not just water ice. It is believed that these materials ejected by cryovolcanoes come from underground reservoirs and rise to the surface, a bit like lava on Earth. But these are much colder materials and they are not rock. It has also been observed that the surface of Titan appears relatively young because it doesn't have many impact craters. Partly this is likely due to its atmosphere, which, like ours, eliminates smaller asteroids by disintegration. But it is also because there is geological activity on Titan. It seems that new material is expelled from the inside of the moon, presumably by these cryovolcanoes, in large enough quantities to slowly replace surface materials over a span of several million years. This activity erases traces of impacts and refreshes the surface. One question about Titan was raised when its unique set of conditions and composition became better known. Is there the possibility of organic life on this moon? On the surface, this sounds very unlikely due to the temperature. But like other moons of the solar system, such as Europa, the moon of Jupiter, there could be subsurface oceans under the thick ice sheet. And in these oceans, maybe, the prerequisites for simple organisms or prebiotic conditions could be present. As of today, there is no evidence that Titan harbors any kind of life, and if it does, it would have to be life that relies on other energy sources than sunlight. Like the life forms on Earth that depend on hydrothermal vents near the ocean floors for the energy and nutrients they need. This is theoretically possible. In a strange way, despite its vastly different materials and climate, Titan is considered to be the body in the solar system that is most similar to Earth in geographical terms. However, its surface is constantly plunged into darkness. At this distance from the sun, even if it could be seen through the atmosphere from the surface, it would only be a very distant and faint light in the sky, not the big shiny ball we are used to. Let's now take a look at the second biggest moon of Saturn, Rhea. Rhea aligns much more closely with our perception of the moon. It's composed of rock and ice and has a scant atmosphere, just a very tenuous layer of gas. It is significantly smaller than our moon and was discovered 20 years after Titan by an Italian astronomer, Cassini. Hence, the Cassini-Huygens mission was named in honor of the early discoverers of Saturn's moons. Rhea may not be as remarkable or as original as Titan, but it holds one record. It is the smallest body in the solar system that has been precisely measured to experience hydrostatic equilibrium. But what does that mean? Planets and moons are round to a certain size, while smaller bodies can be irregular. There is no instance of a body the size of Earth, for example, that would be elongated or irregular. But why is that? It is because of hydrostatic equilibrium, a concept from fluid mechanics. Under the solid crust of planets or moons lies a viscous fluid, composed of very hot material, generally rock and metal. Gravitationally, the reciprocal attraction of all this matter keeps it as one single object. The internal gravitational force exerts pressure on the material at the center of the body, and this weight from the outer layers of matter compresses the center. If this gravitational force was not counteracted, the body would collapse on itself. The mass would remain the same, but it would become increasingly smaller because the matter would become more and more compact. This doesn't happen because there is an opposing force that causes materials to expand, a pressure gradient force. The volume of the body stabilizes at the point where these two forces cancel each other out. Large objects in space tend to become spherical because of this equilibrium of forces. The spherical shape ensures that forces are evenly distributed around the center. This, however, only applies to large-scale objects that are not entirely solid. Small or medium-sized asteroids are not affected by this because they aren't viscous and are not large enough for gravitational forces to compress them or melt their cores. The pressure gradient force and the equilibrium it forms with gravitation are also crucial for the Earth's atmosphere. Without resistance to gravitation, the entire atmosphere could be pulled to the ground and would not be as thick as it is. On the other hand, without gravitation, the Earth's atmosphere would expand around the planet and diffuse into outer space. Our atmosphere maintains its current state because of this hydrostatic equilibrium. You may recall when I mentioned earlier that Saturn is almost as voluminous as Jupiter, but only possesses a third of its mass. How's that possible? This occurs because the mass and the size of the body do not always coincide. It may seem logical that if you make a planet heavier by adding more material, it will become larger. However, this is not always the case. The size of a planet could decrease even if you add more material, because this addition affects its hydrostatic equilibrium due to an increase in gravitational force. In this respect, Rhea is remarkable because it is the smallest known body in the solar system currently under the influence of this hydrostatic equilibrium. As a result, Rhea has a spherical shape. Had Rhea been just a touch less massive, it would likely have adopted an irregular shape. Let's now explore another moon discovered by Cassini, Iapetus, named after a Titan from Greek mythology. Like various other moons of Saturn, Iapetus is similar in size and estimated composition to Rhea, mainly ice with a lesser amount of rock. At first glance, Iapetus appears spherical, but it is not. It falls just below the hydrostatic equilibrium threshold. As a unique feature of this moon, its poles are squashed, and it has a long and high ridge or mountain chain across the equator, giving it an appearance similar to a walnut. Given the size of the moon, this mountain chain is impressively high, reaching up to 20 kilometers. That's almost 12.5 miles. This is more than twice the height of Mount Everest, on a moon much smaller than Earth. For comparison, Iapetus has roughly the same surface area as Australia. There's no clear explanation for how this ridge formed, but several hypotheses have been suggested, including the collapse of a ring system, ejection of icy material from inside the moon, or it might be a remnant from its formation stages as evidenced by its ancient impact craters. Another mystery about Iapetus is its unusual coloration. One hemisphere is dark and the other very bright, a stark contrast that has puzzled astronomers ever since the moon was observed up close. There are several theories, including one that suggests falling material on one of its sides from another smaller moon of Jupiter, Phoebe, is responsible for the distinguished difference in color. Before we continue our journey, let's take a look at one more moon, one with a truly unique feature, Enceladus. Enceladus is small, not large enough to be spherical, and has an ellipsoid shape. In other words, it is shaped like a sphere compressed on both sides. If you put a ball in a press and flatten it, you get an ellipsoid. Due to its small size, it was hard to see from Earth and was discovered in May 1789 by a German astronomer, Herschel, over a century after Titan and Rhea. Nonetheless, Enceladus is one of the most reflective bodies in the solar system, reflecting light primarily because its surface is covered in ice. The ice remains fresh and clean because a large part of it is renewed by frequent cryoeruptions from cryovolcanoes. Enceladus is thought to host subsurface liquid oceans and is another moon considered to possibly have conditions favorable to biological life. No surface life like on Earth, but life in the depths of dark oceans under its icy crust. So, how can we estimate what these distant moons are made of? Some of them have been approached by probes, but we certainly haven't been there to take samples. These estimates come from several different methods. The first is based on the size and mass of celestial bodies. The size can be observed and the mass can be inferred from their influence on other bodies due to gravity. These calculations are complex and involve many factors and unknowns. However, astronomers and mathematicians have been dealing with these celestial mechanics problems for centuries. By combining size and mass estimates, one can gain an initial idea of what a body might be made of. For instance, if it's very massive or heavy for its size, this suggests it contains heavy materials like metal, or if it's light, it might be composed of ice or lighter rocks. The second method involves spectroscopy, which is the observation and measurement of the spectrum of light. Different elements have unique spectral signatures as they emit at varying electromagnetic wavelengths. So we can determine a lot about the composition of distant bodies by measuring these wavelengths. However, this method isn't foolproof because the signals are often faint, especially for distant bodies, and can become mixed. So they require careful analysis. A third method involves combining all this data with what we know about the chemical composition in their environments and formation models. We know, for example, that heavier elements tend to migrate towards the core of a planet, while lighter elements tend to stay closer to the surface. We also know that certain conditions of pressure and temperature determine matter's state: solid, liquid, gas, or others. I'll discuss metallic hydrogen more when we delve deeper into Saturn's surface. So, with these sources of data and the interpretation we can do with them from the various disciplines that astronomy touches on, such as physics, chemistry, mathematics, optics, and spectroscopy, we can build solid hypotheses about what planets and moons are made of and how they are structured internally, even without having physically traveled there. Still, these are only theories and not certainties. There may be changes in the future, as there were some in the past. But at this point, they are the best informed guesses we can make based on available information. As we continue to approach Saturn, it is now time to talk about its rings. The 4 moons we quickly looked at are farther away from the planet. But as you know, because you have seen pictures of Saturn, the rings start quite far from the planet too. They are gigantic, and actually they are even bigger than the pictures suggest, because what we see in photos or artist views is just the most visible ones, the densest, the shiniest parts of the rings. In reality, they extend tens of thousands of miles, more than the planet's radius. These rings are also incredibly thin relative to their size. Thickness varies from 1,000 yards, which is less than a kilometer at most, to only 30 feet or 10 meters. This is not even the proportions of a sheet of paper. The rings are incredibly thin. However, we see them very well, or at least the rings that are relatively close to the planet. This is because they are also very shiny and made almost exclusively of ice, with barely any dust, less than 0.1%. The main rings are made of billions upon billions of particles and small objects. The largest ones are only a few meters or yards across, and they are all little satellites that orbit the planet together. This ice is clean enough to reflect sunlight, and this is why we see the rings so well. Another fact that could sound counterintuitive is the minuscule amount of water or matter the rings contain. The total mass of the rings has been estimated, and it is less than the Antarctic ice sheet on Earth. For comparison, we have to imagine the ice sheet of the South Pole from the Earth. spread on a surface and area that is 80 times larger than the total surface of Earth. That's how thin and delicate these rings are. But why are they so big? How and when did they appear? Historically, the dominant hypothesis was that the rings dated from the formation of the planet or close to it. This suggests that they were billions of years old. This hypothesis was not based on very solid measurements or models, and it was increasingly challenged, especially a few years ago when the Cassini spaceship explored the rings. The rings were revealed to be far less massive than once thought, and it was also confirmed that they regularly lost some of their matter that fell to Saturn. This means that these types of rings come with an expiration date. They will get depleted eventually. The problem with the old rings theory is the shine they possess. Over time, they should have collected cosmic dust particles that would have darkened them. But as I've mentioned, they are made of 99.9% pure water ice. So, from these observations, it appeared that the rings could be much younger, perhaps only 10 to 100 million years old, which would be a small portion of Saturn's existence. And based on current observed depletion rates, the rings may disappear in 300 million years. The edge of the rings is something, but it doesn't tell us how they have formed. Here we have two main theories. The old one suggests that the rings are left over from the original nebula material from which Saturn and the whole solar system formed. All these particles would have turned into satellites of Saturn early in its formation process, and so the planet would always, or nearly always, have these rings. As we mentioned earlier, this theory is now rather old-fashioned because it fails to explain why the rings would be pure ice, and it doesn't take into consideration depletion of the rings into account. Probably because this was not known when the theory was proposed. The second, more recent dominant theory suggests that the matter the rings are made from comes from an old moon of Saturn. The orbit of this moon could have decayed, meaning the moon tended to fall towards its planet instead of maintaining the same direction from it. Once it was close enough, the gravity from the Saturn's large mass, or tidal forces as they are called, would have ripped apart this moon. It would have been shattered over time into all these small pieces that stayed in orbit and formed the rings. A variation of this theory proposes that it was not tidal forces, but a collision between the moon and a comet, or a large asteroid that shattered it. This corresponds with the relatively small quantity of matter in the rings. You may remember that these contain less material than Earth's southern ice sheet. However, this theory doesn't reconcile well with the composition of the rings, which is almost purely ice. This is because there is no example of a pure ice moon anywhere in the solar system. Granted that there are floating blocks of water ice, and water is abundant on many moons. However, even the moons with the most water, like Enceladus, which we visited earlier, still contain about 20% rock. So, if a moon was shattered near Saturn, why did its ice stay in orbit while its rock disappeared? This gives rise to another variant of the same origin theory for the rings. Instead of an entire small moon, it might have been just the ice mantle of a larger moon, possibly the size of Titan. Such a moon's orbit would have decayed during the formation period of Saturn. Its ice mantle would have been stripped and remained in orbit, while the rest of the moon would have fallen into Saturn and been absorbed by it. Still, these remain theories, each with their own merits, and nothing is definitively proven. For instance, the brightness of the rings and their purity are cited as evidence that the rings are young, not hundreds of millions of years old. But perhaps the darker material could have settled in certain areas of the rings. They are not uniform. There are divisions between them and zones that appear more or less bright. Perhaps clumps form within the rings with impurities, and then they get disrupted by impacts, effectively cleaning up the rings. We can't be certain. Thus far, the most plausible hypotheses for the presence of all this matter in orbit around the planet remains a shattered moon, either wholly or in part. The biggest dilemma is discerning when and how this happened. You're likely familiar with the ring's appearance and how they resemble distinct stripe-like subdivisions. There are lines that are more or less bright and sometimes feature entirely dark spaces in between them. These subdivisions have been named based on their appearance and distance from Saturn. A commonly used categorization begins with ring D, the one closest to Saturn, which is quite faint and was confirmed only in 1979 by the Pioneer 11 probe. Proceeding outward, there are rings C, B, and A, each with divisions between them. The nomenclature becomes less intuitive when moving further away from the planet. The ring after A is named F, followed by E. Each of these different divisions has unique physical characteristics like thickness and particle density that make them either more or less bright. Let's continue our approach towards the imposing mass of Saturn. Despite appearing almost as big as Jupiter, Saturn has less than 1/3 of Jupiter's mass. This discrepancy comes from the unique equilibrium of mass and size we discussed earlier. Jupiter, being more massive, is also more compressed, hence significantly denser than Saturn. When comparing chemical compositions and structures, if we leave aside the density difference, the two planets share many similarities. Both are gas giants believed to have a metallic and rocky core, surrounded by enormous layers of gas held together by gravity. The term gas is used here because hydrogen and helium, the main constituents, reflect the nebulous composition from which the solar system originated. Primarily hydrogen, followed by helium, the two simplest elements were most abundant. The so-called trace elements were present in tiny proportions. But Saturn is not like a mere cloud. Its density is far greater. The planet has a core believed to be surrounded by a layer of metallic hydrogen. Hydrogen that is so compressed that it transcends a liquid state. This unique state is called metallic, due to its ability to conduct electricity, a topic we previously covered during our space cruise to Jupiter and its moons. Above this layer of metallic hydrogen exist zones of liquid hydrogen and liquid helium. It's only above these that a genuinely gaseous outer layer begins. Consequently, parts of Saturn are denser than anything you'll find on Earth. Although Saturn has 95 times the Earth's mass, for comparison, Jupiter has over 300 times. When averaged out with these less dense outer gas layers, Saturn's average density is lower than water, about 30% less dense. In its entirety, it could be deemed a relatively light planet. However, Saturn isn't solely composed of hydrogen and helium. Its core, as mentioned, is believed to be metallic and rocky, with traces of other elements present. These other elements contribute to the planet's yellowish hue, generated by crystals of ammonia in its upper atmosphere. Saturn's surface appears more uniform and less feature-ridden than Jupiter's, with a hint of more yellow around the equator. It might be hard to discern in pictures, but its shape isn't strictly spherical. This is due to its rotation and its relatively low density. The rotation creates a centrifugal force, and this flattens the planet a little bit. It becomes an ellipsoid, like Enceladus, the moon we visited before. Except contrary to Enceladus, Saturn is not a body with a solid surface. It is a rotational ellipsoid. It takes this ellipsoid shape due to its rotation. If the rotation stopped, which is not going to happen, but let's say it would theoretically, then the centrifugal force would dissipate, and the planet would become a sphere. Due to this hydrostatic equilibrium that we talked about before, that would no longer be held altered by the rotation. Much like other gas planets, Saturn doesn't have a distinct surface. Upon diving into it, one would gradually encounter increasing gas density, which after hundreds of miles of travel towards the planet's core becomes dense enough to transition from gas into a liquid state and subsequently metallic. At the core, there is a mass of heavy material, predominantly iron and rock silicates. Saturn's distance from the Sun contributes to the longer time it takes to complete one revolution, referred to as a Saturnian year, almost 30 Earth years. The view of Saturn from Earth changes a little during this long revolution due to the varying angles of perception, at times from above, sometimes from below the rings, made possible because all planets orbit around the Sun and sit on the same plane, albeit inclined slightly differently. Saturn's orbit around the Sun is slightly more elliptical and inclined by just over 2 degrees relative to Earth's orbital plane. Therefore, taking the Earth's orbital plane as a reference, Saturn crosses it twice in 30 years, appearing alternatively from above and then from below. Despite its peaceful surface appearance, Saturn houses some of the solar system's most violent winds, reaching up to 500 meters per second. Only Neptune's winds are known to exceed this speed. For comparison, Note that the speed of sound in our atmosphere is 360 meters per second. So, Saturn's winds are surprisingly supersonic. Saturn's southern pole is home to a unique feature, a warm polar vortex, a rotating gas region the size of Earth, around which blows the planet's fastest recorded winds. Heat, believed to emanate from inside the Sun, is ejected from this vortex, despite the average atmospheric temperature of Saturn being measured at minus 185 degrees Celsius, which is minus 301 degrees Fahrenheit. The temperature inside the vortex is approximately minus 122 degrees Celsius, which is 187 Fahrenheit. 60 degrees Celsius or 140 degrees Fahrenheit warmer, but still freezing. These temperature disparities likely explain the violent winds surrounding the vortex. There is much more that could be said about Saturn, with some people dedicating their entire lives to the study of this planet. So, how far are Uranus and Neptune from us on Earth? You remember from our previous space stories that there is a unit that is useful to figure out distances in space, the astronomical unit. It was defined roughly as the equivalent of the distance from the Sun to the Earth, which is about 150 million kilometers, or 93 million miles. Light takes about 8 minutes to travel this distance, and the astronomical unit is convenient to compare distances between the orbits of the planets. So, the Sun to Earth distance is 1 astronomical unit. The Sun to Mars is 1.5 units. Jupiter, which is the 5th planet from the Sun, is at a bit more than 5 astronomical units. Saturn, the 6th planet, is almost twice as far as Jupiter, 9.5 astronomical units. But to reach Uranus, we need to double that distance again, about 19 astronomical units. 19 is like the middle point because the orbit is not a perfect circle. It is slightly elliptical. At its closest, the distance is a bit more than 18 astronomical units, and at its farthest, a bit more than 20. But a good order of magnitude to bear in mind is that Uranus is 19 times farther from the Sun and Earth, and Neptune is 30 times farther. At this distance, light and heat from the Sun take more time to reach them, and there is much less. They don't have a solid rocky surface, as you know, so we cannot really say that they have a cold surface. But the upper layers of these planets are extraordinarily cold. We will see how cold when we approach them. The first close images we got from Uranus are not very old. They were taken by a probe, Voyager 2, in 1986. And they reveal the planets that look almost featureless, without the kind of cloud bands and storms that are observed on other giant gas planets. Neptune looks more animated, but both planets have conditions in their upper layers that are some of the most extreme in the solar system. So first, let's talk about what they are made of and why they are called ice giants. Until the 1940s, astronomers distinguished 2 main types of planets in the solar system: the rocky ones with solid surfaces like Mercury, Venus, Earth, and Mars, and the gas planets, which are bigger and do not have a clearly defined surface because they are made of gas in various layers, denser and denser as you move towards the center. And their core is believed to be made of rock and metal, around which gas has accumulated and remains kept together by gravitation. There were 4 gas planets: Jupiter, Saturn, Uranus, and Neptune. It was assumed that their composition was more or less similar, mainly hydrogen and helium, the 2 most abundant elements in the solar system, and most probably in the entire universe in general. They are the simplest, the smallest types of atoms. There are heavier elements, dozens of them, including some that are also relatively abundant, like oxygen, iron, and carbon. But it is believed that these elements are mostly younger than hydrogen. Like other heavier atoms, they would tend to form in stars when they approach the end of their lives. You know that the fuel of stars is hydrogen. Inside them, hydrogen is exposed to such extreme conditions that fusion happens. Atom cores combine to form heavier atoms, mainly helium, for most of the star's life. But when the end of the star nears, because it has consumed a large part of its hydrogen reserves, which takes hundreds of millions of years, billions of years, in the case of a star like the Sun, the star starts consuming helium, and heavier elements are formed. It is believed that this is how these heavy elements appear all the way to big atoms with dozens of particles like gold or uranium. And then, when the star dies, it becomes gigantic. It explodes in a supernova, which would disperse these elements, and they will become available to form new systems. Our system is much younger than the estimated age of the universe. So, if these theories about the universe, stars, and the formation of a star system are accurate, it is not surprising that these heavier atoms are actually present in our solar system, either alone or combined with other compounds like ammonia, carbon dioxide, sulfur dioxide, or water. But still, most of the solar system, if we take into account the Sun itself and all the planets, is still mostly hydrogen, and to a lesser extent helium. And as it happens, these are also the main components of gas planets like Jupiter and Saturn. They probably have rocks and metals in their core, and they have other compounds in smaller quantities in their various layers, but this isn't much in proportion. So, until about the 1940s, it was assumed that Uranus and Neptune, because they were giant planets with no defined surfaces like Jupiter and Saturn, had a similar composition. To put figures on this, it is estimated that Jupiter and Saturn are more than 90% hydrogen and helium. But it appeared through spectroscopy and estimates of their mass relative to their size, and later measurements sent by probes, that no, Uranus and Neptune were quite different in their composition, only about 20% of hydrogen and helium by mass, and a lot of compounds like water, hydrocarbons, and ammonia. These different compounds are called ices in astrophysics and planetary science. When they are independent from a larger body, like a planet, and at a sufficient distance from a star, They are generally found frozen as solids. On Earth, when we hear the term ice, we typically think about water ice. In contrast, astronomy utilizes the term ice to refer to a broad range of compounds, including water and many others. These compounds share a common trait. They freeze at or near 100 kelvins under Earth's surface pressure. One such compound is water, which freezes at 273 Kelvin, equivalent to 0 degrees Celsius. The Kelvin scale is similar to the Celsius scale, except that it commences at 0, which represents the lowest possible temperature. In contrast, the Celsius scale starts at minus 273. So water freezes at 273 Kelvin, or 0 degrees Celsius. Ammonia freezes at 195 Kelvin, which is minus 78 degrees Celsius. In comparison, methane freezes at 91 Kelvin, or minus 182 degrees Celsius. These elements make up the majority of the mass of Uranus and Neptune, which is the scientific reason why they are called ice giants. However, this term can be a bit misleading, because when we hear ice giant, we may think about a planet with a hard surface, which they are not, or one with blocks of ice floating in its atmosphere, which they also do not have. The term ice refers to the compounds they are made of, not the state they are in, because, as we will see, these compounds are no longer solid. They might have been solid when the planets formed, but they no longer are. This term was needed to differentiate these planets from gas giants like Jupiter, because their composition and formation history were quite different. The term ice giant sounded appropriate, which is why it was adopted over the past 40 years. Now, a good question is, why are some planets rocky, while others are made of hydrogen and helium, and others of ammonia, water, and methane? And why is there an apparent order in the solar system, with 4 rocky planets in the inner part of the system, then 2 gas giants made of hydrogen that happen to be the 2 largest planets, Jupiter and Saturn, and after them, 2 ice giants, which are in between rocky planets and gas giants in the terms of size and mass? To answer this, we need to discuss the theories of planet formation. One factor that makes studying the formation of planets challenging is that we only have one system at our disposal, ours, and it doesn't include that many planets. In our system, only 8 bodies are considered massive enough to be classified as planets, plus a few smaller bodies like Ceres or Pluto, which are considered dwarf planets. But overall, not that many. The starting point of a star system is relatively uncontroversial among astrophysicists at this point. Although it remains theoretical, it is backed by numerous observations concerning the chemical composition of planets, their orbits, the laws of gravitation, and even the direct and confirmed observation since 2018 of a star in formation around a newly formed star named H.L. Tauri. This star is situated 450 light-years away from us, which is considerable, but not that far on a cosmic scale. A star system is believed to form when enough matter, including gas and dust originating from a nebula, accumulates within a small space. A nebula is an immense cloud of matter floating in space, several of which exist within our galaxy. The primary force driving the formation of a star system is gravitation. Within this region of space, the suspended matter tends to form a large disk rotating on itself. An initial impulsion is necessary for this rotation to commence, and it is believed that supernovas, the final explosion of stars, could provide this as they generate shockwaves in space. As this disk rotates, matter tends to concentrate faster and faster towards the center, and it increases, absorbing more and more matter. When this mass reaches a critical point, where the pressure at the core is sufficient to trigger fusion, it transforms into a star. Typically, this new star undergoes a brief period of growth, during which it absorbs most of the disk's matter. In the instance of our solar system, the star consumed more than 99% of the total matter. We know that there are systems with several stars, 2 or 3 of varying sizes, highlighting that diverse models of aggregation are possible. But the single star model, like our system, is the most common. In any case, while this leaves little matter available, there is typically still enough to form several planets, which absorb the remaining matter from the protoplanetary disk, what the star hasn't engulfed. This protoplanetary or accretion disk forms the basis of planetary formation models. Nevertheless, theories explaining the specifics of planetary formation vary, especially for ice giants. Their existence posed a significant challenge to existing theories when their composition was discovered. The formation of rocky planets like Earth and gas giants like Jupiter is not very controversial. They are widely understood to have formed through millions of years of collisions of smaller rocky bodies within the protoplanetary disk, until one larger planet remains on its orbit, having cleaned up the orbit of all other bodies. But why do some planets become gas giants instead of terrestrial planets? The reason seems to be that these would have formed larger solid cores at approximately 10 times the Earth's mass. Consequently, with a stronger gravitational pull, they would also accumulate through accretion an envelope of gas. Observations within our solar system suggest that rocky planets are closer to the star, while gas giants are further away. This led to the supposition that the distance from the star helps retain gas. So, for a long time, it was believed that gas giants had to form relatively far from the star, from the center of the system, whereas rocky planets could occupy more central positions. Though they could theoretically exist throughout a large part of the protoplanetary disk, they would tend to become satellites or moons of gas giants, if in close proximity to their orbits. But in the last 2 or 3 decades, this theory or assumption has been challenged by numerous observations made outside our solar system. With an abundance of exoplanets found in other star systems, it has been seen that there can be large gas giants or exoplanets orbiting close to their star, with very short orbital periods. In other words, they complete their orbits much more quickly around the star, taking only a few days compared with a year for Earth or 12 years for Jupiter. The discovery of these gas giants close to their stars led them to being referred to as hot Jupiters, named for their proximity to the star. Undoubtedly, their existence presented a challenge to existing theories about gas giants. These planets were the easiest to discover due to their size and closeness to their stars, resulting in a significant number of hot Jupiter discoveries. Consequently, the theories were revisited. Currently, the prevalent understanding is that hot Jupiters probably form far away from their star, then migrate closer to it. The migration could be gradual due to an imbalance in the system until they find stable orbits closer to the star, or it could occur due to a collision, causing a sudden change in their trajectory in space. An alternative hypothesis is that they form in situ, close to the star, possibly due to a particularly large solid core that exhibits significant gravitational pull. The truth is that this remains an open question at this point. But returning to ice giants, when it comes to the formation of ice giants, existing models, though effective for explaining terrestrial planets or giants like Jupiter, struggle with deciphering the formation of these large planets located so far from the star. Why is that? Accretion of a rocky core requires collisions, plenty of them. For the formation of a protoplanet to occur, which progressively clears its orbit by absorbing everything within it. So, at the start, the protoplanets are rather small. A theoretical issue here is that, given their distance from the star, a protoplanet forming in the orbits of Uranus or Neptune should have been expelled when they were smaller in the solar system, following the laws of gravitation. It makes sense that planets like Jupiter or Saturn remain within the system. They are at 5 and 9.5 astronomical units from the star, respectively. The farther you are from the Sun, the less you are bound to the system by gravitation. The force diminishes with distance. At 20 units, like Uranus, or even more at 30 like Neptune, combined with the accelerating effects of Jupiter and Saturn, the protoplanets would have exceeded the escape velocity. In other words, they would have traveled fast enough in space to overcome the Sun's gravitational pull, and should have ventured beyond the solar system, or been absorbed by Jupiter and Saturn, or transformed into comets before fully forming. However, they evidently did not, because they exist. Yet the existence of a planet that formed via collision at 20 or more astronomical units from the Sun and remaining on a stable orbit is something current formation models struggle to explain. To further complicate matters, it seems that Uranus and Neptune are not the only exceptions. Many exoplanets discovered in other systems are strong candidates to be ice giants. So what could have occurred? A possible first scenario is that they might have migrated after their formation, much like the suspected behavior of hot Jupiters. these planets could have begun to form somewhere between the orbits of Jupiter and Saturn, 5 to 10 astronomical units from the Sun, and then altered their orbit at a time when their size and speed were sufficient to keep them bound to the solar system. It is not precisely explained how. There are various theories about this outward migration. For instance, it might have been due to close encounters with Jupiter or Saturn, which would have expelled them to another orbit. Another possibility is that they formed differently, near their current orbit, but in that case, it couldn't have been through collisions. An alternative that could work theoretically would be that the ice giants formed due to instability in parts of the protoplanetary disk. There could have existed regions of slightly higher density in the disk, which could have led to the formation of clumps of matter. These clumps would eventually collapse due to gravitational forces, forming a planet. Models suggest that a disk with a bit of instability could yield protoplanets between 10 and 30 astronomical units from the star, and both ice giants of the solar system are within this range. At this point, the formation of Uranus and Neptune is explainable. The thing we don't know is the specific mechanism of process, for those processes may have been very different. As we approach Uranus, now 19 astronomical units from the Sun, we see that although it is much smaller than Jupiter and Saturn, it was still observable from Earth centuries ago, perhaps as early as antiquity. However, for a long time, it was mistaken for a star or a comet. It wasn't until the late 18th century that several astronomers, noting that due to its movement they realized it couldn't be a star and had to be a planet beyond Saturn. Uranus is about 19 times farther from the Sun than Earth, as we said, and has also slower orbital pace, so it takes much more, 84 years, to complete one revolution. Actually, since its identification as a planet in 1781, it has completed fewer than 3 full orbits. And also, as I mentioned earlier, we should note that it receives much less sunlight than Earth due to its distance. The intensity of sunlight varies inversely with the square of distance, meaning it decreases faster and faster as you move away from the Sun. Consequently, at around 19 or 20 astronomical units, depending on where the planet is on its elliptical orbit, Uranus receives 400 times less light than Earth. In other words, Uranus travels through space in the dark. If we look at the Sun from Uranus, it would appear as a small point in the distance, not the large, bright light that we see from Earth during daytime. Uranus has many moons. 27 have been identified to date. We will explore the largest of them, Titania. But before we do this, let's start our journey from the planet's atmosphere and travel inward to its core. Now, what we call the atmosphere is merely a gaseous envelope, since there is no well-defined solid surface on Uranus. The atmosphere has been identified as the region accessible to remote sensing, up to 100 bars of pressure. This covers a region that is still hundreds of kilometers or miles within the planet. We saw earlier that the pictures taken from Voyager 2, or lower definition telescopes suggested a peaceful, quiet, and featureless planet, which appears as a pale blue-green. This coloration results from the composition of the atmosphere, which absorbs red light. However, this impression may be misleading. In truth, the planet's atmosphere is quite active. For short periods of time, such as the 2 months in 2004, large clouds can form in the atmosphere, accompanied by spectacular storms. Record-breaking winds at over 500 miles per hour, or more than 800 kilometers per hour, have been observed. Though the climate isn't perfectly understood, it seems to be subject to significant variations. Since the 1990s, and thanks to advanced imaging techniques and different types of light, have revealed many clouds and atmospheric phenomena. The atmosphere mainly comprises hydrogen and helium, which account for an estimated 20% of the planet's mass. These elements are believed to be absent from the denser parts of the planet. The third element that makes up a bit more than 2% of the atmosphere is methane. The aquamarine color of the planet in visible light is probably due to methane. This atmosphere is intensely cold. Temperatures fluctuate based on altitude, but the coldest part regions of the troposphere, that is to say, the lowest and densest part of the atmosphere, they can reach near 50 Kelvin, below minus 200 degrees Celsius, or below 350 degrees Fahrenheit. The atmosphere on Uranus is less well known than that on Earth, but it's established that in the troposphere there are different layers of clouds where the pressure is lower. They appear to be made of ammonia, hydrogen, and sulfur. However, at higher pressure points, these clouds could be composed of water. These different levels of the troposphere have a highly complex and dynamic structure, with strong winds and seasonal variations. Below the troposphere, density and temperature increase, and progressively, hydrogen and helium diminish. And we come closer to a kind of mantle composed of ices that give their names to this type of planet. Although these ices aren't truly solid, they were probably solid before the planet formed. These compounds are referred to as ices because they would solidify if they existed in open space, as on a comet, or on the surface of a rocky planet. This mantle represents the majority of the planet's mass. In total, Uranus's mass is more than 1.5 times that of Earth. The gaseous envelope of the planet, despite occupying a lot of space, is intense. The mantle, which is denser, amounts to more than 13 Earth masses, or about 90% of the whole planet. Given the conditions, the main components, which are thought to be water and ammonia, are thought to be in a state of dense and hot fluid. This fluid state is sometimes referred to as water-ammonia ocean. By the way, you know what water is, but what is ammonia exactly? When hydrogen forms molecules with oxygen, you get water, as you know. Ammonia is a molecule that hydrogen forms with nitrogen and is abundant in the solar system. There is some on Earth, but it can be found in much higher quantities on Mars, Jupiter, Saturn, and, of course, Uranus and Neptune, where it is an important component. While it is found only in trace amounts in nature, on Earth, and is often associated in salts with other elements like chloride or sulfur, it plays a critical role in the cycle of life on our planet. It is a common byproduct of aquatic organisms' feeding processes and contributes to the nutritional needs of terrestrial organisms. Plants need it to grow, and it serves as a precursor to almost half of the world's food. Typically, fertilizers contain some. Returning to space, the mixture of water and ammonia, notable for its low freezing point, 173 Kelvin, which is minus 100 degrees Celsius, or 100 degrees less than water alone, could act as an antifreeze in other environments and facilitate the existence of liquid internal oceans at temperatures far lower than would be possible with water alone. However, it isn't a concern for Uranus, as a temperature where this water-ammonia mixture exists on the planet is estimated to be much higher. Where the mantle begins, the temperature hovers around 47 degrees Celsius with a pressure of 100 bar, meaning 100 times the atmospheric pressure at sea level on Earth. Farther inside the mantle, both temperatures and pressure continually increase, reaching extremes at the center of the planet at an estimated 8 million bars and a temperature of approximately 5,000 degrees. A hypothesis suggests that within the mantle, methane, which is also present, could be broken up. Methane is comprised of hydrogen and carbon. Therefore, pure carbon atoms could potentially condense into diamond crystals that rain through the mantle, in a manner akin to stone sinking in a lake. However, this isn't a lake of water, but rather a mixture of water and ammonia under very high temperatures and pressures, superior to those in the deepest abyss on Earth. These diamond rainfalls may not exist solely on Uranus. Theoretically, they could also occur within Jupiter, Saturn, or Neptune. Another hypothesis is that there may be an ocean of liquid carbon at the base of the mantle, where the core begins. In this state, it is termed metallic carbon, due to its electric conductivity. Yet another curiosity would be the presence of water at such high temperatures and pressures that it transforms into something called superionic water or superionic ice. This refers to a state where conditions are so extreme, unattainable on Earth, that water molecules break apart and oxygen crystallizes. That is to say, it adopts a highly organized, repetitive structure resembling a lattice. In between this lattice, hydrogen can float freely. This phase of water existed only theoretically until it was successfully synthesized in a laboratory very recently, in 2019. During the experiment, water was squeezed between two diamond pieces and maintained at very high pressure. It was then blasted by a pulse of laser, creating a pressure of 1 million times greater than atmospheric pressure. It's staggering to conceive of, but the pressure inside Uranus could theoretically reach up to 8 million atmospheres, as we said earlier. So it is possible in natural conditions on this planet. The water was heated almost instantly with the laser to several thousand degrees, recreating the conditions believed to exist within the mantle of Uranus and Neptune also. As expected, the oxygen and hydrogen in water molecules broke apart, and the oxygen crystallized. This phase of water is also termed Ice 18. In a previous discussion about the moons of Jupiter, we contemplated the various types of water ice that might exist under different conditions. Ice 18 is one more, and it may exist in a stable state in the depths of ice giants, even though we are unable to go there to sample and verify this hypothesis currently. After the mantle, the last part of the internal structure is the core. It is around this core that ice and gases aggregated during the formative process, or to where heavier elements possibly migrated. This is not entirely known, as I previously mentioned when discussing the planet's formation history. The core is believed to be relatively small, roughly half the mass of Earth, and is likely composed of silicate rocks, that is, silicon and oxygen, in addition to various metals. Now that we have quickly seen the inside, let's take a look at the periphery of the planet because there are more things to see there. First, there are rings. They are not very visible and generally not represented on views of the planet, but 13 of them are known. The majority of them are very narrow, only a few kilometers or a few miles wide, and they are made of very dark particles. These particles vary in size from microscopic to 1 or 2 feet. It is believed that these rings are younger than the planet itself. Some theories suggest that one or several moons may have been shattered by impacts and left their matter in orbit around the planet. With Uranus, we know it hosts a respectable number of moons. There are 27 of them. So let's focus on the largest one, Titania, which is also the 8th largest moon in the solar system. It is believed to have formed, much like the other moons of Uranus, from a small accretion disk that surrounded the protoplanet during the early stages of the solar system. In its composition, Titania is very similar to several moons of Jupiter that we visited during one of our space journeys. It has rock in the center and an exterior envelope of water. It's unknown whether some of this water could be liquid under a crust of solid ice. Titania is relatively small, much smaller than the Earth's moon, and it may not have retained enough internal heat to support underground oceans, subsurface oceans, like those suspected to exist on Europa or Ganymede. On the surface of Titania, there are abundant canyons. These aren't features that could be created by asteroid impacts. Canyons can form due to plate tectonics, but Titania is too small for that, or they could be caused by erosion. Yet Titania doesn't really have an atmosphere where meteorological events that would provoke erosion. So a hypothesis is that long ago, there may have been a liquid ocean on Titania's surface, under a layer of ice. It may have remained liquid thanks to the presence of ammonia. As we said before, ammonia, when mixed with water, is a powerful antifreeze because it freezes 100 degrees Celsius below water alone. Then, as Titania cooled down, this subsurface ocean would have frozen, making its volume increase. Such a process could have created surface canyons, as it would have broken the hard ice crust. Overall, Titania is an icy desert. It doesn't generate much internal heat, there is no atmosphere to retain the heat, and it receives minimal sunlight due to the distance from the sun. Nevertheless, there are still temperature variations due to seasons which are extremely long, due to a unique characteristic of Uranus. Uranus has the unusual trait of presenting its pole to the sun rather than its equator like other planets. This is thought to be the result of a major collision in the past that would have tilted the planet. The moons orbit around the equator of the planet, and Titania always presents the same face to Uranus because it is tidally locked to it. This means, in terms of seasons, is that when Uranus is on one side of the sun, Titania presents one of its poles to the sun, and when Uranus orbits to the other side, the opposing pole is exposed. Furthermore, given that Uranus takes 84 years to complete one orbit around the sun, this means the seasons on Titania last 42 years. One side is bathed in light for 42 years, whereas the other half remains dark. After this period, they switch for another 42 years. Uranus is about 20 astronomical units from the Sun. To reach the orbit of Neptune, we need to travel 10 more astronomical units. Neptune, as we're about to see, is near a twin of Uranus, but with a few differences. Neptune is so far away that it is invisible from Earth to the unaided eye. This is why it was the first planet discovered not by observation, but by mathematical prediction. This happened in the first half of the 19th century. Uranus had been found and was observed by telescopes, and its orbit was mapped. However, something was off. There were unexpected changes in the orbits of Uranus that weren't really explainable by the existence of other planets and the laws of gravitation. So either there was something wrong with the calculations, or there existed yet another unknown planet that influenced the orbit of Uranus. The position of a possible eighth planet was deduced from the perturbation of Uranus's orbit, and this ghost planet was tracked in the night sky until 1846, when it was found. In the following decades, several moons were found around Neptune, starting with by far the largest one, Triton. We'll take a look at it a bit later. In terms of composition, structure, and size, Uranus and Neptune are thought to be very similar. With an envelope of hydrogen and helium, ice is inside, that is to say water, ammonia, and methane, to a lesser degree, carbon dioxide. But in visible light, Neptune looks bluer. This is believed to be due to more methane in the upper layers of the atmosphere and possibly another component that has not yet fully been identified. Another difference is that Neptune is a bit more massive than Uranus. It has 17 times the mass of Earth versus 14.5 times for Uranus. While it might sound counterintuitive, Neptune is also physically a bit smaller. This is due to its mass, which implies a bit more compression of its atmosphere. In balance, it has a bit more matter in a bit less space. Another difference is the distance to the Sun. The two planets are 10 astronomical units away from each other, a huge distance that is about the same as the distance from the Sun to Saturn. This means even less sunlight. Neptune, because of its larger mass, is internally a bit hotter. So the temperature at the center is estimated at 5,400 Kelvin versus 5,000 for Uranus. Despite this, its atmosphere is one of the coldest places in the solar system. The temperature approaches 50 Kelvin, which is below 200 degrees Celsius, and only 50 degrees above absolute zero. Since its discovery, Neptune has completed only one orbit around the Sun. It takes 165 years, twice the time Uranus needs. Yet another difference is the intensity of meteorological activity. Compared with Uranus, Neptune's atmosphere is far from peaceful. There are giant storms constantly, a complex system of clouds, with the most powerful winds in the entire solar system. They blow constantly at more than 1,000 miles per hour in the upper atmosphere. This is believed to be a consequence of the temperature differential between the core and the mantle, which are hotter than those of Uranus, and the atmosphere, which is cold in its upper parts. As you know, winds are produced of gas masses moving from one place to another due to a differential in pressure and temperature. And on Neptune, these differentials are bigger. And so the planet looks constantly agitated by giant storms that have been observed since we have been able to produce higher definition images. For a time, there was a big dark spot, comparable in nature to the great red spot on Jupiter, which is a storm. It eventually disappeared, but more perturbations are constantly appearing and disappearing on the surface. Beyond Neptune begins a region called the Kuiper Belt, a very large region of the outer solar system, teeming with millions of smaller asteroids. Pluto, the dwarf planet, is one of these bodies. The edges of the Kuiper Belt have been set from 30 astronomical units away from the Sun. That is to say, Neptune's orbit to 55 astronomical units, and Neptune strongly influences the Kuiper Belt due to its gravitational pull. It has shaped its structure over time, after hundreds of millions of years and millions of revolutions around the Sun. This is evident in the number of objects that are in orbital resonance with Neptune in the Kuiper Belt. I explained the concept about Jupiter's moons because 3 of them are in orbital resonance. To summarize, it occurs when 2 or more objects on different orbits become locked by their respective influences on each other, with their revolutions occurring in a stable ratio. In the example of Jupiter's moons, every time Ganymede completes 1 orbit, Europa completes 2, and Io completes 4. So they are set to be in a 1, 2, 4 resonance. Similarly, Neptune is in resonance with dozens of smaller bodies in the Kuiper Belt, starting with Pluto. They are in a 2, 3 resonance, which means when Pluto makes 2 revolutions, Neptune makes 3. Other ratios have been found with other bodies, such as 3-4, 3-5, 2-5, 4-3, 4-7. Over time, the Kuiper Belt has come under the strong influence of Neptune's mass and orbit, in a manner akin to the influence Jupiter has on the smaller asteroid belt lying between the orbits of Mars and Jupiter. Neptune also has 40 known moons, most of them small, except for one, Triton. Triton alone represents more than 99% of all objects orbiting Neptune. All other moons combined do not even comprise 1%. Therefore, let's focus on Triton because it possesses unique elements and aspects that distinguishes it from most moons. The first of these is its retrograde orbit, meaning it orbits in the opposite direction to Neptune's rotation. This is a very rare occurrence for large moons in the solar system. Most of the time, they follow the rotation of their planet, exhibiting prograde motion. This is a strong indication that Triton did not form in Neptune's periphery, but was captured later, possibly from the Kuiper Belt. Had it remained in the belt, it would have been considered a dwarf planet, similar to Pluto. Triton is slightly larger than Pluto and nearly as large as Earth's moon, making it quite sizable. In fact, the 7th largest moon in the solar system. Its surface appears to have been renewed, as suggested by the density of impact craters. There are few. This strongly indicates that if the moon can renew or rejuvenate its surface, it is geologically active. That is to say, it has a differentiated structure with a core, mantle, and crust that would be coherent with its size. Moreover, there seems to be 2 types of geological phenomena at the surface: cryovolcanism, meaning eruptions of warmer materials like water that surge and subsequently freeze on the surface, and tectonic activity, which releases other materials from inside the moon or allows plates of the crust to move. This is how mountains and drifts can appear. How can a body of such size be captured, bearing in mind the vast distances within the Kuiper Belt? Several possible mechanisms exist. Nonetheless, it likely required a very long time and perhaps millions of orbits around the Sun. Parts of Triton's orbit may have intersected or neared Neptune's. Neptune's gravitational pull could gradually have slowed Triton, reducing its speed below the escape velocity, allowing its capture by gravitation. This slowdown could also have resulted from the collision between Triton and an ancient Neptune moon, now vanished. Alternatively, Triton could have formed a binary system with another body, like Pluto and its largest moon, Charon. Neptune's influence on this system could have led to an interaction that pushed Triton into an orbit around Neptune, with its partner expelled from the Kuiper Belt, or even possibly from the solar system altogether. We don't know. But it seems that Triton's arrival had catastrophic effects on Neptune's ancient moons. It disrupted their orbits, potentially causing collisions, and the gravitational interactions could have scattered smaller moons when the system stabilized. Triton constituted more than 99% of the mass orbiting Neptune, the rest being faint rings and small irregular moons. At the surface, Triton is enveloped in a layer of frozen nitrogen. In this region of intense cold, it may also hold a water envelope accounting for 15% to a third of the moon's mass. Beneath that, a mantle and a core of rock and metal could be present. Like many moons we have visited in our stories, there might be liquid water, a subsurface ocean, that could theoretically harbor life. However, this is speculative, and it's already hard to imagine an expedition to Europa or Ganymede, which is 5 astronomical units away from the Sun. Triton is 6 times further at 30 astronomical units away. The idea of launching a manned expedition to explore it remains science fiction. At this point, it takes a lot of patience to send probes to these regions of our solar system. All space missions take time, but this is really far. You remember we talked about the probe Voyager 2, for instance, was the first NASA probe to capture nearby images from Uranus and Neptune. Launched in 1977, it reached Jupiter in 1979, then Saturn in 1981. And finally, after an additional 5 years and despite accelerating speeds, it reached Uranus in 1986. And still continuing to accelerate, it reached Neptune in 1989, 12 years after its launch. Voyager 2 remains active and is now on a mission to explore interstellar space, 44 years after departure. The distance Voyager 2 has traversed is absolutely mind-blowing. When it reached Neptune 32 years ago, it was at 30 astronomical units from the Sun. Then it traversed the entire length of the Kuiper Belt, which concludes at 55 astronomical units, eventually exiting the solar system's zone of influence at 120 astronomical units in 2018. Voyager 1, also built for interstellar exploration and launched almost at the same time, is still operational and currently is at more than 150 astronomical units from Earth. These 2 probes are by far the human man-made objects that have traveled the furthest ever. We have finished our full tour to the ice giants. If you wish to visit other space destinations, we have more stories in our library for your enjoyment. But for now, you can let go and fall asleep. And until we meet again, good night. Sleep well.